welcome back. All right, team. It is 5:18. I think it's a good place to start. So, final exam. It's been a little bit more than a month since the last time we were here. Okay. I hope your exams are going okay right now. I heard there was an exam today for first year CPS 8 something. No. Which one? 1 something. Anyway, so yeah, that's why we started a little bit later today at 5. I wanted to start about 3 p.m., but it's okay. So the final exam study hall today is going to be shorter than the midterm study hall. 2 reasons. It's Saturday. Okay. Second reason, it's less content to cover than the midterm. Midterm has a really chunky portion to cover, especially a lot of theory for crystal structures, planes, all that good stuff. Today we're going to cover all the chapters that you covered after the midterm, and we're going to do a lot of practice questions. Okay, a lot of good practice questions. My emphasis today will be on practice questions more than theory. I'm going to go and talk a little bit about theory, of course. Yes, just to familiarize you with the chapters. For the final exam, so we're going to have 60 multiple choice questions on Monday and 7 long problem questions. You're going to have a choice. You will be able to select 5 questions out of 7, okay, for your final exam to solve. Those are long problem questions, so you will need to fully write down your solution, okay? So I'll show you what is expected when professor checks your solution. Okay, you will need to show some amount of work. There's a minimum amount of work expected. Okay, even if you get your answer correct, and if you don't show the process, you will be getting less marks. Okay, so there's no reason for this. I will show you exactly what you need to follow for all the types of questions. We're also going to cover some questions from the midterm chapters because we didn't have time last study hall. Cool. Any questions beforehand before we start? Yes.
Yeah, just for the long answer.
Yes.
Is it like if I do all 7, do they mark what like?
You only need to select 5. You don't need to do 7.
I have to personally tell them which one.
Yes, yes, yes. You just leave the blank sheet and like obviously you didn't solve it, right?
So if I solve all 7, they're not going to pick what's best. I can still tell.
No, I mean you're not allowed to write 7 questions. Okay, they're not going to be selecting. They're going to mark from 1 to 5 then. Okay, I mean the 2 questions that you might get right or wrong. Well, I mean just select 5 that you're most confident in and then do it. Okay, even if you know how to solve all of them, just 5. Okay. All right. Any other questions? Nope. I guess. Okay. All right. All right. Let's begin. So, question.
Is there any previous exam posted?
Previous exams, guys, are not posted. There is no previous exam available. All the exams are being guarded, okay, every year. I don't have access to them, unfortunately. And even if we did, they would be kind of like, I guess, useful but useless at the same time. They're not going to be recycled at all. Every final exam every year is new. Okay, every question, multiple choice, every long problem question, new. Okay, and they're not from the textbook. You'll not be able to textbook. Or just come up with those questions and put them on the final. Okay, don't worry. There's going to be nothing super complicated. The questions are all derivatives of each other. Okay, I will show you the questions that appeared on final exams in the past 4 years. Okay, and those are the types of questions that you will need to expect to see. Okay, there's going to be nothing new. Okay, you will all be able to see it during the study hall and during the practice section. Okay, of the questions. Any other questions? Nope. All right, awesome. Let's begin then. So. Yes, final exam is cumulative, so a couple of housekeeping rules, blah, blah, blah. Chapters 2, 3, 4, 5, 9. Those are midterm chapters. And 12, 14, 16, 17. Okay, those are going to be our ceramics, polymers. Those are going to be our the fiber composites and corrosion. Okay. Alrighty. Blah, blah, blah. Some regular stuff. Yeah, so I'm recording the video as well. It will be posted right away on YouTube, probably around like 10 p.m. or something. Today's agenda. Okay, blah, blah, blah. Yeah, so again, my emphasis is going to be today on practice questions to solve. And I will cover a little bit of theory questions. And good stuff. Let's begin. So the chapter right after the midterm was covering polymers. Ceramics. Okay. So what are ceramics? You're familiar by now with all the metals, crystal structures of metals, FCC, BCC, CCC. Should know it pretty well by now. The theory, a good portion of the metal stuff is going to be attributed in this chapter as well. So ceramics do possess also FCC, BCC, and HCP. Okay. There are a lot of different variations of ceramics, okay, because you do not expect the same atomic bonding, okay? We don't have metallic atomic bonding when it comes to ceramics. We do have ionic or covalent. And either ionic balancing on each other, and it's with each other, and it depends a lot on the ratio of RC over RA. C stands for cation, and A is anion, okay? So crystal structure is purely influenced by the electrical charge of ions and the relative sizes, okay? This is what defines the mechanical properties, physical properties of any ceramic, okay? How big ion or anion we have in our crystal structure, okay? And also another important distinction with metals. In the midterm chapters, we always talked about pure metals, such as iron, zinc, silver, and so on, right? If you go and talk about alloys, I was talking here months ago about the steel alloys, right? We have iron and carbon. So iron is going to be the larger atom, okay, that is going to be occupying the BCC crystal structure. And carbon is the smaller atom that is going to be occupying interstitial sites of the BCC. So it's going to be somewhere in between the big atom in the center and the neighboring atoms in the corner, okay? So when it comes to ceramics, we're always going to have a particular chemical structure, cesium sulfide, fluoride, and so on. There's going to be never a pure structure when it comes to ceramics. Well, the same way with metals. So what we're going to see is the crystal structures, which are going to have different elements inside. One is going to be larger, one is going to be smaller, and this will reflect on the size of the unit cell, okay? In metals, when we had our atoms being the same, let's say, radius, obviously the same diameter, we have iron in BCC, so we can predict what they're going to be the unit cell length in the BCC structure, aluminum for FCC, and copper for, anyway, blah, blah, blah. So for this particular type, the equations for the unit cell length will change, okay? Because, again, that depends on the radius of atoms within the unit cell, meaning that cation are going to be different radiuses, which means that is going to affect the length as well equation. So each cation prefers to have as many nearest neighboring anions as possible. Yeah, so that's basically just reducing the randomness in your alloy. Again, the nature wants to possess the lowest state of energy as possible. Okay, so we want to occupy as many electron shells as possible to have the most stable structure. Okay, so this is the 2D geometry of how the ceramics look like. So we have obviously, if the ceramics need to be obviously in touch with anion and cation in order to produce the most stable structure. The unstable structure like this will dissolve and diffuse into something else to create something stable. Simple stuff. Okay, this one I took from the textbook. It basically kind of tells you that the radius of the cation, and those are the red or pinkish volumes, the spheres, and anions are the ones that are smaller ones, okay? And obviously the coordination number is going to be reflected. So the larger we have the difference between cations and anions, the less amount of the neighboring atoms we're going to have. So as we increase this amount, we're going to have a coordination number increase as well, okay? You don't need to memorize these numbers in particular. But I'm going to talk a little bit later about what exactly you need to memorize for all of this. Okay, so size of ion depends on the following criteria. So radius increases the number of the opposite charge, and the charge of ion. Okay, so the radius of the ion increases with the ions of the number of electrons. Okay, so in ceramics, we need to create a stable structure. So if we have cesium sulfide, okay, we have a particular amount of cesium electrons, sulfide electrons. They need to balance out. Basic high school chemistry stuff. Okay, so for ceramics, we have 3 particular types, and you do need to remember them for your final exam. Okay, AX type, AMXP, and AMBNXP. Okay, what do these letters mean? AX means that you have like sodium chloride, let's say. It's a very stable structure which has just from sodium, one chlorine, and you form AX type. Okay, AMXP would be something that has a valence of 4 or 2, and the other one has a valence of 1, so even odd number. Okay, so for something like this, basically. So AX2 subdivision, so calcium fluoride, for example, okay, all that stuff comes on final exams more often. I don't remember that ever the AMXP type. It's sodium chloride, cesium, sulfide, all of that stuff usually is what appearing on final exams, okay? So a very important thing that you need to remember about AX type that mostly all of them are FCC structures. Okay, FCC. So on the final exam, when you're going to be given a question about, let's say, sodium chloride or any of the substances, cesium chloride, for example, okay, those 3 good examples, they will not tell you what the structure is. Okay, you will have to know that it's FCC. All right, so that's the key point. And obviously, if you get the structure wrong, you're going to have your coordination number wrong, amount of atoms wrong, and the density will be wrong as well. A typical question in the final exam is to calculate a, let's say, density or the atomic packing factor, okay, for AX type. That's what I have seen in the past final exams. So take a note of this. And we're going to solve a couple of questions as well on this. Okay, so cesium chloride, for example, this one is, so there is a mistake here, guys. Okay, correct it, please. It should be 2 RC plus RA. Okay, so that's from last year. I haven't corrected yet. We'll come back to this equation as well. So zinc blend structure, all that good stuff. All right, AMXP type. So those are the ones that you should know. This could be your multiple choice question. Okay, so you might be asked about the coordination number for AMXP type, and how many cations and what kind of ratio you may expect. So just read it, please. In the book, again, it takes a lot of pages to read all of this, so I took some effort and fully simplified it and put it right here. I have seen in the past some multiple choice questions asking about AMXP type or the other type. Okay, so just memorize the keywords, okay, and that would be a good help for you. All right, so most of the crystal structures for ceramics do possess FCC structure. It could also be simple cubic. Okay, so if we get back to our AX type, okay, all right, bring in more chairs. All right, so for the cesium chloride structure, okay, this one is going to be simple cubic. That's something you have to memorize as well. Okay, I think 2 final exams ago, was that 2 years ago? Yeah, we had a question about this. It's simple cubic. Okay, we're going to have a question about this as well. I'm going to solve it. Yeah, pretty much. So let's move on from this. Good stuff, good stuff. All right, closed pack-in anions. Okay, so similar to, obviously, as metals, we're going to have our closed pack directions, closed pack planes, all that stuff. We don't need to worry about all of that for these chapters, okay? So all you have to know is that we have tetrahedral and octahedral positions, okay? So that also could be one of the multiple choice questions, and I think I've seen it last year. What are the coordination numbers for tetrahedral positions and octahedral positions, okay? Pretty good question on the final exam. Okay, a couple of things. Ceramic crystal structures depend on, okay, the stacking of anion closed pack layers. So we have a cation, we an anion, all those spheres. How are they creating our closed packed planes? So we have the stacking sequence, okay? Similar to HCP, we have AB, 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 FCC is AB, C, AB, C. Again, ceramics do possess the following, the exact same behavior. So we're going to see the exact same manner as in chapters for the midterm for metals. Yes, so interstitial sites that the anions are occupying. As I said, have a BCC structure. If we have a smaller radius of another atom, they're going to want to go and diffuse into interstitial sites. Okay? And cations reside in octahedral positions. So those are mainly large atoms. Okay, it will be in the center. It will be mainly in the center, basically, such as BCC. Okay, for example. So ceramic density calculations. Again, the story is the same as in metals. For the atomic weight, instead of one pure metal, we're going to have cation and anion, okay, because we have two different elements within the crystal structure. Okay, so we'll have to add the atomic weights of both. All right. The volume of the crystal of the unit cell stays the same. Avogadro's number. Again, the equation does not change. Okay, and about the equations, you're going to have the equation on the final exam. Okay, it's going to be provided on the back. You are expected to know the equations. Okay, they're not going to be labeled as what exactly the is. Okay. They're going to be scattered over the page, so you do need to know what the equation you're looking for. Okay, you kind of should if you do practice questions. So yes, and there's going to be a lot of equations because chapter 16, the composites is quite a lot to cover there for equations. But yeah, you should hopefully know this equation by now. All right, silicate ceramics. And the book covers particular cases of different ceramics. So this could be asked on the final exam question. That is why I put it here as a pretty good summary. So for silicate ceramics, the question could be like, what type of atomic bonding exists in the silicate ceramics? So it's a non-covalent bond. Okay, that's something you need to memorize. Pretty good question to be asked on the final exam as well. Yes, it has the subdivisions: silica, silica glass, the silicates, so all that good stuff. Okay, I also gave some examples of the silica oxide, silicon oxide, electrically neutral, resembles low densities, quite high melting temperatures. We have silica as well. Okay, what else we have here? Positively charged cations serve two roles, compensate the negative charges. Again, give it a read, guys. Okay, you will not need to memorize all of this, but if you're familiar with the sections of or the particular subdivisions of silica, okay, that'll be really helpful for you. Again, the book covers a lot of stuff, so I was trying to make it simple for you and emphasize the main key points. So give it a read after the study hall before the final exam, okay, on Sunday tomorrow, and just make sure you're familiar with this stuff. Okay, carbon. Carbon is also a very typical question to be asked in the final exam. I guarantee you're going to have one of the questions on carbon. Yes, so the question will be, what are the three forms of carbon exist in nature? Okay, so we have two allotropic and one state. Okay, so what does allotropic mean? It could be, so allotropic is something that possesses a very particular crystal structure. Okay, so what are the types of carbons that we know in nature? It could be diamond or it could be graphene. Okay, sorry, graphite. Graphene is a particular layer sheet of a graphite. Okay, so essentially graphite is comprised of a lot of layers of graphene. Okay, and amorphous state. So what is amorphous state? Amorphous state is not necessarily liquid, obviously. It's carbon going to be in different forms. So it could be soot. Okay, it could be coal. Okay, mainly why we call it amorphous is because the carbon in those physical structures does not have a particular pattern. Okay, we know that the pattern exists for diamond. Okay, there's going to be a particular pattern here of how the atoms are arranged. This is what gives the highest hardness in nature that we know about. Okay, graphite the same. It's going to be sheets. Okay, of the sp2 hybridization. So they're very van der Waals bonds, very much weak. With pencil on the paper. Okay, and there's a coal, something like some soot, which is contaminated with silicon, sulfur, and all of that stuff. Okay, so this is very important to know. All right, I also made a summary of some important distinctions. Yes, so this is what I refer to as graphene. Okay, it was successfully separated by scientists about 20 years ago. Just one simple two-dimensional sheet of the graphite, and it appears to be pretty strong, actually, on its own. In fact, from my search on the graphene sheets additions into aluminum silicon copper alloys. To publish a paper on that. Pretty good stuff. All right. And wonder why forces exist in the graphite. Okay, that's very important. This region particularly is what gets separated when you apply even the slightest shear force. Okay, so these things go onto your paper when you write stuff. All right. Well, obviously, the exact same story. We have imperfections in solids, in metals. Well, guess imperfections do also exist in ceramics. Okay, so we're gonna have our point defects. We're not going to be talking in these chapters about the directional defects or and volume. Well, defects are obviously possible, but the stuff gets pretty complicated when you talk about planar defects. So in this course, we only restrict ourselves talking about point defects. Okay, so those are going to be our Schottky and Frankel defect. Okay, so when you have a vacancy, we have a large line missing. That's going to be our Frankel defect. Defect is missing our small interstitial site. Okay, actually, sorry, the other way around. Frankel is the interstitial site. Schottky is the large line. So interstitial and regular vacancies. Okay, so very simple. You can apply this same logic from your midterm chapters here as well. Okay, and our lovely phase diagrams. Okay, yes, they also do exist. Okay, and they're pretty in ceramics. So we're not expecting from you to memorize those phase diagrams at all. And on final exams, you are never asked about ceramics phase diagrams. It will always be your metal phase diagrams. Okay, question?
If you go back to the first
imperfections.
Okay.
Yes. All right, we've got a question.
The other question is just a drawing that says which one is which, or
you're not going to have a drawing. It's going to be, the question could be, I'm not saying it will be, it could be that what is a Schottky defect? Okay, A could be, you know, a pore, like a volume defect. So some trash, and one of the answers is going to be interstitial, okay, or yes, so again, Schottky defect, again, is Ni missing, so it's interstitial. Again, it's the same thing as a metal. Right? We were talking about vacancies and interstitial sites. We're calling them now Frankel and Schottky defects, okay? Actually, in metals, you can only call them the same, okay? But again, the question could be like, what is a Frankel defect? A, interstitial side of an ion. B, you know, the other stuff, you know. Question?
What is the difference between an anion vacancy and a Schottky defect?
Schottky defect, okay. Schottky defect is going to be, again, our vacancy. So it's going to be the large atom. And again, the Frankel defect is the exact same thing as metals. Okay, names. Yes. Sorry, my bad. Yes, yeah, that's right. So the anion is bigger and titanium is one smaller. Yes. So anyway. It's the exact same as the metals. Okay, we have interstitial and we have the vacancy. So it could be that you have again, in ceramics, it could be random stuff. You might have two different things missing at the same time. It's okay. Yes, it's still a Schottky defect. That is correct. Yes. Well, let's go back. I'll show you the. We have the ratio of RC over RA is mostly less than 1. Right? So what does it mean? That a 9 or a 9 is going to be always bigger? A 9, right? A 9 is going to be always bigger, right? So that means that, okay guys, can you keep it quiet please kindly? Thank you so much. Yes, so RC over RA is the ratio that defines all mechanical properties, okay? So a 9 is going to be the one that is always going to be at time, okay? Because of the ratio. Okay, and that's how we differentiate all the mechanical properties and physical properties of our ceramics, okay? Glass and so on, right? So let's return back to Schottky and Frankel defect to clear the confusion over here. And thank you so much for your points. Yes, so when we're missing the interstitial, when we have an interstitial defect, that's going to be the line that is going to be missing. Okay, we have a line that is the Frankel defect is the one that is missing the big anion. We have the definitions over here as well. Okay. And all I need to memorize for the going to be just the point defects. Okay, we're talking about defects. It's quite a cancer when it comes to ceramics. So what it. Okay. Any. It goes to the surface? Yes, let's double check that. Alright. The Schottky defect? Defect. So removing one cation and one anion from the interior of the crystal and then place them on the external surface. What I mean by external surface is the diffusion. So there's nothing much. Don't overcomplicate it. Okay? Okay. Question?
Yeah, so everything about ceramic phase diagram was not on the
Yes, so let's not talk about ceramic phase diagrams. The thing that you might get on the final exam is what I included over here. You know, a ceramic or metals are going to be phase diagrams on the final exam, but this would be a pretty good multiple choice question. Okay, and I have seen a couple of multiple choice questions about this on the final exam. So you do need to memorize, again, it doesn't mean that it's necessarily ceramics, you do need to memorize basics of eutectic, peritectic, monotectic reactions on your phase diagrams, okay? So when we go and cool down our material coming from liquid to two solids, or from one solid liquid to another solid and liquid, okay? Those are the 5 things that I want you guys to memorize, okay? And be able to distinguish on your final exam. You might be given a reaction, actually, the question could be like, which one of the following reactions is the monotectic reaction? Okay, and you're going to have A, B, C, D, E, and then that's going to be one of your answers. Okay, so it's a pretty good multiple choice question to be asked. All right, and so all these reactions are coming from different phase diagrams. Okay, and there's phase diagrams that exist. Actually, like this one, for example, right? There's quite a lot of things going on here. We have our regular eutectic reaction, right? When we have 2 solids, right? We have magnesium oxide in this case and magnesium something else. In metals, it will be, let's say we have a typical metal phase diagram, zinc and silver, or zinc or whatever. The exact same stuff, okay? Nothing changes. Okay, we have 2 solids, we have 1 liquid, or we have 1 solid, liquid, and so on. Okay, I do encourage you guys, please, to memorize this. It could be, if I were the prof, I would definitely put that question on the final. Here we go. Okay, take a note of this. So, what is gamma? One of you might ask. It's another type of solid. Okay, so it's another precipitate. Okay, let's say we have some aluminum, magnesium, and zinc alloy. When we mix them all together, okay, we're going to have aluminum, magnesium reacting with each other. And we're going to have also magnesium and zinc. And we could also have aluminum and zinc reacting. Okay? So in fact, what I just talked about is a regular AZ type alloy of magnesium. Okay? So in reality, obviously, we don't have perfect materials. We don't have pure. We have more than 3 elements. Okay? More than 3 major elements. So you can imagine what type of phase diagram does actually exist for more than 3 elements, right? Because so far, all you know is just the 2 elements. Okay, but when you go into 3-dimensional phase diagram, that's where the fun begins. Okay. Again, for this course, that's all you need to know. Just 5 reactions. You don't need to be familiar with these types of phase diagrams. That's just what the book is talking about. Okay. Plastic deformation. I need to emphasize something there. In ceramics, okay, all ceramics, they do not have a lot of plasticity. Okay? What is plasticity? Plasticity is the deformation. Okay? How do we get deformation? Let's return back to from chapters. We have slip planes. Okay? We have our edge dislocations and screw dislocations. Okay? So those missing or extra planes of atoms are the flaws in the material. They're not necessarily defects. And I want you guys to I want you guys to remember this. It's not a defect, it's a flaw. Okay, defect is when you have a volumetric, let's say, porosity, or there's like literally a defect, an inclusion could be a defect. But those are the flaws. And plasticity is essentially where we start applying the stress on the material, and the material starts deforming by moving those slick planes, okay? And last time in the midterm study hall, I showed you how dislocations are moving. Okay? Dislocations are basically the loose planes and directions of atoms, they just move. And this is exactly what allows the metals to be deformable. Okay, we have copper, super ductile material, okay? And we have steel, like let's say hard worked steel, which is going to be super strong, okay? So it's not going to be that amount of deformable, but it's still going to be strong, okay? When it comes to ceramics, these are completely non-plastically deformative types of elements, okay? So when you shatter a glass, you know, if you apply a little bit over too much of the stress of the yield point, it's just going to shatter instantly, okay? That's because it does not have dislocations to move, or it doesn't have enough, okay? So in this chapter, we say there is some plasticity when it comes to ceramics, but that plasticity depends on the non-crystalline and crystalline ceramics. Again, what I want you to memorize is that the ceramics, such as glass and any ceramics that you know, they are super brittle. Okay? If you were to look on the stress strain curve, okay, you would go very steeply high towards the yield point, and that's where it's going to end. Not that steep, the linear curve, the Hooke's curve, okay, the Hooke's line. You go like this, you have the yield point, and then you go into plastic region. Okay, the plastic region is where you deform. Okay? That's something I want you guys to remember. Ceramics are very brittle. Okay, any questions about this? I'm going to start working on the problem questions now. Okay, question.
Crystalline ceramics are brittle?
Which one?
Crystalline ceramics?
All ceramics. Okay, but the crystalline ceramics are going to be less brittle because they kind of have some particular structure. But overall, what I want you to remember is that they're all brittle. Okay, because it's, you know, how the glass is, right? If you apply a little bit too much of a stress, done, fracture, right? All right, let's begin this question. All right, I uploaded the PDF file onto the Dropbox, so you can guys pick it up on your laptop. Okay, I'm going to read the question aloud, and we're together. All right, so the question is as such. Potassium chloride has a rock-salt structure. Okay, so it's ceramics chapter. We're not talking about different types of metals. Okay, it's going to be sodium chloride, a rock-salt structure. Okay, so if the angle of diffraction for the 200 set of planes occurs at 28.35, first order diffraction, when monochromatic X-rays having a wavelength of 0. Blah 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 nanometers are used, we have to compute a couple of things, okay? So, for your final exam, there's a structure that I want you guys to follow. Please listen carefully, okay? So, these questions are going to be checked by professors, okay? Most of you are from Ravi's class, my supervisor, and you are the ones who I was able to contact because I don't have emails of the other sections. But anyway, all professors expect a bare minimum of having a given. Okay, you are going to have a given. You have to write down what are you given. Then here you're going to have to write down what you're going to be looking for. Your solution will have to be here. Okay, and you will have to show your steps. You will have to show your steps. It is very important. If you just plug in your numbers to the calculator with no process, not good, guys. Okay. One important point as well, you need to show the units. If we're talking about the addition of atomic weight, let's say, if I have a cesium and a fluorine or some stuff, or let's say fluoride, know that that is, let's say, X type of grams per mole plus that type of grams per mole. Okay? Professors are going to be looking for these types of flaws in your solution. They're going to be taking marks off. Okay? So do not provide them as a reason to take the marks off. Please write down all your units, all the numbers, and all the solution. Okay? So do not skip any step. Okay? That's what I want you guys to do. And we're going to be solving all the questions today in this particular manner. Alright? Alright, let's begin. So, this one is good. Oh, nice. It's dirty. Okay, cool. So, potassium chloride has a rock salt structure. So we know we have a potassium chloride. And this question combines two chapters, ceramics and the X-ray diffraction chapter. Okay? So, potassium chloride. Set of planes. Okay? We have the order of diffraction equal to 1. So can somebody remind me, the angle we're giving is 28.35. Okay? That's called the angle of diffraction. What kind of angle it is? Can somebody remind me? 2 multiplied by theta, right? I spent here last time, I think, half an hour, 40 minutes explaining what the X-ray diffraction is. It's on the midterm study hall, okay? When we have the incident light coming in, coming out, that's our incident angle, theta. The diffraction angle is diffraction angle, how much it took for the beam of light or the X-ray photon to diffract, okay? That's going to be another theta. 2 theta, okay? So, do not assume it's 2 theta. So the diffracted angle, the diffraction angle, is going to be 28.35 degrees, okay? 28.35 degrees. And what else we're given? We're given the X-ray photon wavelengths. 0.1541 nanometers. Another important thing I want you guys to make sure you know is your nano, pico, micro stuff, okay? Please memorize them, okay? Your figures should know. Okay, about the molar masses, atomic weights, you're going to be given a on the back of your what do you call, final exam paper, or in your question, you're going to be provided the molar masses. Okay, so make sure to always cross-reference and check the back of the final exam. It's going to have some figures. It's going to have some pictures of polymers, and I'm going to talk about it. Okay, so your polymers, you might not know what polybutadiene ethylene stuff is. Okay, it's going to do the geometry, the geometrical formula. So always cross-reference your final exam data sheet. Okay. All right, the molar mass of potassium is going to be 39.1 grams per mole. And the molar mass of chlorine is going to be 35.45 grams per mole. So, what do we need to find? A couple of things. First one is the intraplanar spacing. Okay? So that's what the DHKL is. Okay? We have one plane of 200, and we have another plane of 200. That distance between the two planes is going to be the DHKL, the D200. Okay? I hope you guys remember that. Just a quick reference. So we're looking for DHKL. Okay. Let me change the marker, guys. It's too dirty. Okay, I think it's better. All right. So we're looking for DHKL. That's going to be part A. Part B will be looking for the unit cell length. Okay. Part C will be looking for density. And part D will be looking for a couple of things we're going to be looking for. So the theoretical unit cell edge length, assuming the potassium ion and the cation ion in contact along the edges, the ionic radii of potassium and chlorine. Okay, so we're giving the radiuses of our cation and anion. This is going to be 0.139 nanometers. And that's going to be chlorine of 8.1 nanometers. And we need to find a theoretical unit cell length, okay, given the radii of each of the elements, okay? So this is what I want you guys, I expect from you to write down when you dissect the question. When you read the question, analyze the question, this is what you need to write down. And now we're going to talk about the solution, okay? So Bragg's law, very simple. We derived it last time. We have n lambda. So for part A, step number 1, n lambda is equal to 2d(200) sine theta. Okay? So isolate for d, we have n lambda over 2 sine theta. we need to look for theta. We have 2 theta, so obviously we're going to take a half of this. Okay, so we're going to get our 0.3145. Okay, we're not going to spend time plugging stuff into calculator. Okay, so that is it. That is our D00. Very simple, just involves one of the equations. Part B, we need to find the unit cell length. Okay, so that one is going to be the that one is going to be the one we need to use another equation. What, guys, equation you remember from the Bragg's law? Okay, how do we relate the Miller indices with the intraplanar spacing and the unit cell length? Okay, what's the equation? Over root, okay. Root of what? Okay, Miller indices squared. Okay, and what do we have on top? A, not 1, A. Okay, that's going to be our A. And A is what we're going to be looking for. Okay, so we simply isolate for it. We have 2D00 times H squared plus K squared plus L squared. That is going to be equal to, okay, so that is 0, 0. That is 2. Okay, that's literally coming from here. Okay, so H squared, 2 square root of it is just 2. So we have 2D0. So we simply have a factor of 2. Okay, so we found this to be 0.3145 multiplied by a factor of 2, and we get 0.629 nanometers. Okay, very simple. Part C, we're looking for density now. Okay, so a quick warm up. What is our density equation? Na over V A. This is what we had for metals. All you have to do now is to add the sigma notation, okay, the summation. That's going to be for ceramics. Okay, so what is the crystal structure of sodium chloride? FCC. All right, so okay, I'm not going to go back and put down the stuff, but it is FCC. Okay, so again, in this question, you're expected to know the rock salt crystal structure. Okay, it's not BCC, not HCP, it's FCC. Okay, you have to know this. If you do not know what a rock salt crystal structure is, well, you're going to assume wrong stuff. Okay, please memorize this. And that's kind of like all about ceramics, to be honest. This chapter is literally just a derivative of metals, and all you have to do is just to memorize a little bit more stuff. Okay. Same stuff. Anyway, so we have, how many atoms exist in the FCC? 4. Okay, so we have 4 multiplied by the summation of the molar masses. Okay, so we have 39.1 plus 35.45. So that's going to be something divided by the VC. So what is our volumetric volume of the unit cell? A cubic, right? Because we already found this. So we simply have to put this number, 0.629 nanometers, all cubic, multiplied by Avogadro's number. So you plug in all your stuff into calculator, and we're going to get a pretty beautiful number of 1.99 grams per centimeter cubic. Okay, that's going to be the density for this particular element, this particular substance. But part D, okay, part D, this is the theoretical density. That is the theoretical density. That was the theoretical cell length. Okay, A, yes. Molar masses. Yes. Yes, you would be given. I just talked about it. Yes, you would be given either in the back of your final exam sheet, or it's going to be given in the question. Okay? Yes. All right, guys, be quiet. No. So what is for theta? You remember? Okay, watch the study hall. We don't have time for this. Okay, but no, for theta is not going to be given to you. You either have incidence angle or diffraction angle. Incidence is just theta. Diffraction is 2 theta. Okay, so incidence. Yes. Yeah. No. Just remember what I mentioned, right? Because you have different atoms. Oh yeah, Well, yeah, because you have a unit cell, like it's a cube, right? Yes. A cube is still going to be A cube, but the equation of how to derive your A out of R is going to be different. Okay? Yes. Multiplied by you have two oxygens, right? Okay, question? All right, guys, please calm down. We have a question. What is the question? 1.99 grams per centimeter cubic. Okay. All right. So the units. Okay, guys, I want you to pay please close attention. You need to include your units. Okay. If you don't, that's going to be marks off. Marks off. Okay. Even if you get your question right. Okay. We have N. That's going to be 4 of what? Atoms. We have 4 atoms multiplied by the grams per mole divided by the nanometer. So what is a nano? That's times 10 to the power of negative 9 meters, or times 10 to the power of negative 7 centimeters. Okay? So that's going to be cubed, multiplied by Avogadro's number, which is the inverse of mole. Okay? So please know your units. You need to show them. Okay? For no reason, you're going to be missing marks for that. Question? So should answers always be given in centimeters cubed? Well, that depends what you're given, right? You can give in whatever units you want, right? But they need to make sense, right? And the easiest way to be the least path of resistance, right? So why do we need to convert it into feet per square, right, or some stuff? Wouldn't it be easier to do nanometers? No, in this question, centimeters. Why? Because, yeah, just do it. You'll see it. It's going to be easier in centimeters, okay? You could leave it in nanometers. It's just weird. When you present your density, it has to be grams per centimeter. Or, sorry, grams per centimeter cubic. Could be also meter cubic. Okay? Question? Not common. Well, A values are grams per mole. There's nothing to convert there. Yes, the volume has to be converted. Yes. 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 All right, question? So, the N's? No, N is going to be the same. It's a one crystal structure, FCC. You have your sodium chloride, you have NaCl residing in your FCC structure. Okay? Okay, that's our regular FCC structure. Okay? You're going to have your sodium and chlorine here. Okay? They're going to be different atoms, but they still in FCC structure. And you have 4 of them in total. Okay? So it's not like metals when we have only, let's say, copper. Copper is going to be our FCC. So it's going to be the exact same atom here, the exact same atom here and here. No. It's 2 different elements in one crystal structure. But there are still 4 of them. I am not sure. I don't know. Maybe. There's like, I don't know. Well, maybe we'll see later. Yes, question. I don't hear you. Okay, guys, you gotta come down, okay? You gotta come down, guys. Okay, question. Okay, I'm coming to you. Okay, I'm coming to you. You will be out. Give me a second. Okay, all right. I have arrived. Yes.
Is it okay for the upcoming question if you write a bit bigger?
Oh, sure, yeah. Yeah, no worries. Sure, I can do that. Good that I came here. All right. Question, sir? Go ahead.
Me?
Yes.
If you're stuck in a question and you feel like you can't solve it, but you want to get marks, if you write down the given and the formula, you get marks for that?
Yeah, you would. Yeah, at least you understood the question, right? But like, I don't know. I'm not going to be marking, so maybe the prof is going to be like, I don't know. But like, ideally, yeah, you should. Yeah. All right, guys, let's solve the part D now. Question. What? N? N is 4. It's the amount of atoms. Oh, sorry. Well, okay. This N is the Bragg's law N. That's what you're asking. Yes, sorry. N is the order of diffraction. Okay. But N in the density. All right, guys. I'm just waiting for you guys to come down, okay? It's really hard to like talk over that amount of people, okay? The midterm was quite a, yeah, you know, my throat was gone after the midterm last time. Okay, so if you could please just kindly, if you want to talk, just you know, not that amount of sound, okay? Good question, yes. N is 1 is the Bragg's diffraction, okay? How many, what was the, yeah, so that's basically order of diffraction. How many planes do we skip in order to make our incident of X-rays, okay? We always assume it's 1 in this course, unless you're told otherwise, okay? But in the density equation, your N is the amount of atoms. Yes, sorry, I didn't get your question right from the first time. All right, part D, okay? That part basically just tells us what is the unit cell length given the potassium and chlorine, okay? Both okay? So, okay, what we'll need to do, we find the A. The A is going to be simply, I'm going to show you guys. The A is going to be simply 2 times RLE Cl minus plus R of potassium plus, okay? So you basically simply add 2 diameters together, and that's going to be 0.640 nanometers, okay? So this is very close to what we found from our Bragg's law, okay? But in reality, when we find the radii of each of the cations, that's going to be this, okay? So I have this in my PDF file, okay? For sodium chloride. Yes, question? No, that's for sodium chloride only, okay? That's kind of what you need to memorize, okay? So that's very important. Okay, this question encompasses 2 things: ceramics, X-ray, density, a lot of good stuff, okay? And it's a very, very typical question on the final exam, okay? And in fact, I was able to reproduce this question from one of the finals, okay? I think it was like 3 years ago. So I kind of memorized it after the final note of it. And this is what it is. You might get similar questions, okay? All right, questions? Yes.
What's for sodium chloride only? You just said that's only for sodium chloride?
It might be for somewhere else. Check my PDF file, okay? But I'm pretty sure for sodium chloride, that's what it is, okay? But again, it depends on the radii of your chlorine and potassium, okay? So, and it also depends what type of the crystal structure it is. We were told it is a rock salt structure. It is rock salt, you see? Yes, question. Yes, no, yes, yes. For particular for sodium chloride, essentially. Yeah, but again, for ES, there are a couple of ones, right? There's cesium chloride, there's sodium chloride, right? But they all have separate ones. Yeah, they all use that same thing. Yes, let me show you. All right, let's go back and check the notes. So, all right, so for rock salt structure, the unit cell relation is 2Rc plus Ra. You need to remember that, okay? Because for the same rock salt structure, if we go to cesium chloride, it's going to be that, okay? And it's no longer going to be FCC. It's going to be simple cubic, okay? Super confusing, I understand. Just you need to memorize that, okay? There's a reason this PDF file, and there's a reason I put all of this stuff here, okay? Again, I was able to fully read the book and fully try to squish the information that you must know, okay? Which is why we have the study hall, okay? That is what you need to know, okay? So, for rock salt, 2Rc plus Ra. You're expected to know this. If I have this on my PDF file, you need to know this, okay? We're going to be, let's say, solving the question, I think, in a moment about cesium chloride. No, it's no more 2Rc plus Ra. It's going to be, it's going to be 2 times Rc plus Ra equal to root 3 of A. There's not 4. It should be 2, okay? Yes, question? Derive it. Like, to show you. Yeah. Yeah, you could. You could derive it. it might confuse you. Yeah, it's not like metals. It's going to be different because you have two different atoms there. So you'll be like kind of confused on how to, get from the diagonal to here and all that stuff. Kind of-ish, kind of. Just memorize it. It's going to be easier. Okay? Yes, question. Sorry. Yes. Format for the line. Oh, but the format is going to be. All right, guys, calm down, please. The format of the question is going to be. The format of the question is going to be simply whatever I just basically, whatever I have in my PDF file. You're going to have 7 questions. Out of 7, you choose 5. Okay? That is it. Huh? And then 60 multiple choice, which you obviously cannot choose. Distribution. Don't quote me on this, but I remember it's out of 100. You have 61 mark each, and you have, I think, 8 marks per question that you choose out of 7. So that constitutes into 100. So 40 questions, 40 points, 5 questions. Okay? All right, let's resume. So, and same blend, okay? So guys, I put 3 structures here, which you do need to know, okay? Whatever is in the red table, okay, that's what you need to know. All right? Okay, we're going to resume. Let's now solve another question. All right, let's see. All right, let's see if we can solve this one. All right, let's do this one. Wait. How's the phone? Good? Okay, I'm afraid I used a permanent marker here. All right, this will have to stay until I remove it later. What a pain. All right, let's now solve next question. It's now engraved in the board. All right, so the unit cell for magnesium, I don't know how to pronounce it, Fe2O4, whatever it is, has a cubic symmetry with a unit cell length of 0.8392 nanometers. If the density of this material is blah, 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 compute the theoretical density for this compound. Okay? So, we need to compute the theoretical density, and cool, and we're given some stuff. All right. I'm going to use this part of the board now. All right. So, same drill. Given. Can you see over there? Yep. Good. Awesome. Fantastic. So, given. What are we given? Okay, this one is better. This one's removable. All right. So we're given a substance of whatever it is. The density of the material given is this. So we need to find okay. I'll have to change this question. I'm going to give you another question, guys. All right. So we're given the same substance. It is going to be magnesium iron 2O4. Instead of looking for the density, which is very simple, we just did one question, I want to change a little bit. We're going to look for atomic packing factor. Okay? So that could be one also of the questions on your final exam. Okay, so we're given the substance. We're also given the density. So we now know the density of this substance is 4.52 grams per centimeter cubic. Okay? And now we need to look for the atomic packing factor. So we need to find atomic packing factor. Okay? So you're going to be given a molar mass atomic weight of each of these substances. So we know we have A of magnesium. Okay, that's going to be 24.31 grams per mole. 31 grams per mole. We have atomic weight of iron. That's going to be 55.85. Oh, also another comment I would like to make. On the final exam, if you have like polymers, like C, H, and N, those are very standard elements that you kind of like should know the atomic weight of. Okay, so it might not be given on the final exam, but you're kind of expected to know your AC, AH, and A nitrogen, let's say. So make sure you know this stuff. Okay, I do not guarantee you're going to have molar masses for this. Okay, so please know this as well, and also oxygen. So A of O. Okay, just in case. All right. So A of iron, and then we also have A of oxygen. That's going to be 16 grams per mole. All right? Okay, so how do we approach this question? Any clue? Let's say it's final exam. You have time limited. What do we do? Density calculations. Okay, so let's write down the density calculation. What is the density equation?
Rho equals n prime the sum of the weights and then the volume of the cube and Avogadro's number.
Okay, what do we know? We know A. What do we know? We know. Do we know? No, not yet. Perhaps. Question. What about this? Rock salt? Is it rock salt?
Depending on the type of salt.
It's some type of salt. So we cannot guarantee it's FCC. We cannot guarantee it's BCC, nor ECP. Right? So what do we do? Rock salt? 1 second. I have a different question here, so I'll need to change it on the thing. Okay, disregard that assumption in rock salt, okay? So, in the question that I have, I'm going to switch it later after the study hall. You're not given that it's rock salt. That's another challenge, okay? You're going to have to figure out if it's rock salt or not, okay? So, let's say we don't know it's rock salt. What do we do? I mean, guys, we also know what the density is, no? Right? Okay, and we need to find the atomic packing factor. What's the equation of atomic packing factor? Vs over Vc, and what is the Vs? Volume of what? Sphere, and over the volumetric, or over the volume of the unit cell, right? Okay, awesome. So we need to find essentially what is going to be our Vc, okay? We need to find our Vc, we need to find our Vs, we need to find our N, and then from there we're going to be able to find our APF, okay? So it's quite a procedure to follow here. All right, so let's write down a solution here, and I will walk you through step by step. All right, solution. All right, step number 1, we have our density equation, NA summation of A Vc over NA. We need to find N, okay? So from N, we'll be able to determine what kind of the substance it is. Is it rock salt? Is it something else? Okay, so to find N, we need to multiply density by Vc by Na, divided by the summation of your atomic weights. So the atomic weights are, all right, let's put it all down together. We have 4.52 grams per centimeter cubic. Okay, so what is going to be our Vc? Right? Are we given the... Okay, so we were also given in this question atomic, the unit cell edge length, 0.836 nanometers. I missed it? Okay. So otherwise you would not be able to figure it out, right? So given unit cell length, so we so far do not know what kind of crystal structure it is. It's some random location of this substance, okay? So Vc is going to be simply our... Okay, we plug it into our density, isolate for amount of atoms, okay, per unit cell. Then from there, we're going to be able to figure it out. So we have meters. We need to convert it to centimeters, okay, because we have density in grams per centimeter cubic. Okay, so don't forget about that. Do not just simply plug. So we have 0.836 times 10 to the power of -7 centimeters, all cubed, multiplied by 6.022 times 10 to the power of 23rd mole inverse divided by the summation of all the atomic weights. So we have 1 magnesium, we have 2 iron, and we have 4 oxygen. So to find the sum, we just simply go A of magnesium plus 2A of iron plus 4A of oxygen. Okay, after you plug in all these numbers, we get 8.0, roughly, 4 milliunits per unit cell. So basically atoms per cell. Okay, that's going to be our N. All right, now figure out what do we have, or that's not really atoms, that's just the formula units. So formula units means that we have 8 of the magnesium, 8 times 2 of iron, and 8 times 4 of oxygen in one crystal structure, okay, of this substance in total, okay? All right, so when we look for N, that's going to be amount of formula units per cell. Because it's not just a pure copper or not a pure iron, okay, because if it was just a simply pure copper, then we know it's going to be 4 atoms of copper in total in that crystal structure, okay? But in here, we will have to fit in this type of ceramic, okay? So we'll look for N, because we do need to compute for atomic packing factor. What is the unit cell volume that the atom is occupying in the crystal structure? Okay? And then we'll have to divide it by the VC, the total volume. Essentially the efficiency of the packing in our crystal structure. Given this, let's do step number 2. Now we need to compute the VS. Okay? How do we compute the VS? Volume of the sphere, 4/3 pi r cubed. Okay? We know how many atoms are of each of the elements in this structure. And we also know how many of the units we expect per cell in that structure. So in order to compute our VS, I'm going to move on over here. In order to compute our VS, okay, we will need to multiply. Okay. Okay, also radiuses of those elements we also need to write down. That's also going to be given to you. Of magnesium 2 plus, that's going to be 0.072 nanometers. So that's something you will have to go into the back of your final exam sheet. Okay? So that's, again, something important. If you're missing something, always cross-reference the back of your final exam sheet. Okay? So we have R of iron, 2 plus. That's going to be, 3 plus. That will be our 0.069 nanometers. And we have iron, or radius of O2 minus. Okay, that's 0.14 nanometers. Okay, so those are the 3 things we need to go and look for. After this, we go back into our equation. Okay, so what do we know about, okay, so we have 8 of formula units per cell. Okay, so we have 8 magnesium atoms inside the crystal structure. So 8 times the volume of magnesium plus 8 formula units of iron, but we have twice the iron inside the ceramic. So 2 times whatever we need to have from the N number. Okay, so we have, again, the structure of ceramic is magnesium, iron 2, O4. Okay, so we have 2 times N number, which is 8, times the volume of iron atom, given the radius. Plus, we have 4 elements or 4 oxygen atoms per one substance. And we need to accommodate this 4 atoms of oxygen within the 8 formula units per unit cell inside this crystal structure. Okay? So we need to add 4 times 8 times volume of oxygen. It should be 3 plus, should be 2 plus, and 2 minus. Okay? Don't forget the details, very important. So we have to do a lot of number crunching. We know the volume of the sphere is 4/3 pi r cubed. We know what the pi is. We know what the 4/3 is. We have our radii of the elements. We plug it all in. Okay, this is going to be 4/3 pi r of magnesium 2 plus cube. This is going to be 4/3 pi of r iron 3 plus cubed. That's going to be 4/3 pi r O2 minus cubed. Okay? After you plug it all in, we get the number of 0.02 times 10 to the power of negative 22 cubic centimeters. Okay? Again, you will have to convert nanometers to centimeters. Why? Because, well, you could also leave it in nanometers if you wish, because we have A also in nanometers, okay, over here. And we know that the unit cell volume is going to be A cubic. Okay, so if you just simply leave 0.836 in nanometers, and you leave all of these, convert to nanometers, then it's going to be fine. Again, keep the same units, okay? All right, so after all this tedious process, we can compute our atomic packing factor. That is going to be our Vs over Vc. And after you divide all these numbers together, you get 0.688. Okay? And you can report this number in percentage, or you can leave it in a fraction as is. Okay? Okay? So we have about 70% of the packing efficiency in this particular structure. Okay? Now, the reason I wanted to switch this question is because it's a very tedious question, and it could be one of the questions on the final exam as well. It's a pretty solid question to be asked. Yeah, so it's pretty good. Any questions, guys? Question? Yes? It's not volume of sphere, it's the volume of spheres. All of the atoms. No, well, I guess, yeah. Call it a big sphere. The content of all the atoms that occupy the unit, so it's essentially. Pretty much, yes,
Why did you go money instead of VC?
That's my C.
Oh, okay.
All right.
On the written part of the final, units in each area.
Yes.
So like.
Yeah. You have to. Yeah. It's just better if you do it. Yes.
Like most of the time, every year they change up the question.
Yeah. Well, you're not going to get quantum physics, as I've been telling people. It's going to be maybe different numbers, kind of. I mean, the equations will have to be the same, right? I mean, you cannot change the equations, right? You just, I mean, what I can tell you, right? All right, guys, calm down. The question is, right? Are you going to be given, like, you act like super great question? No. I mean, if I am a professor, I have a certain set of questions, a certain set of equations, let me put it this way. I have the density equation. Okay? What can I change in this density equation? Not much. I have atomic weight, constant, Vc, A, that's what? A crystal structure. Okay, so I can play around with the crystal structure. A is a constant. Density, well, I can either look for density or I'm given density. N, again, is dependent on the same thing, the crystal structure. The density will be also dependent on the crystal structure. So all of this goes down to what? The crystal structure. So we have the midterm, FCC, BCC, HCP. We have our A, okay, types. We already know about this. Now we have ceramics. We just need to memorize 3 more things. What kind of A goes into cesium chloride, sodium chloride, and something else. Okay? So how many questions can I make out of all of this? Maybe like 5, maybe like 6. So you can ask AI, okay, I have this question. Go create 6 questions for me that have different parameters that I need to look for. Done. That's all your practice. And now you have to repeat it probably 20, 30 times for other questions. And you do it for all of them, and guess what? 100% in the final, I guess. No, not really. I have multiple choice questions. Right? All right. Doesn't take a genius, okay, guys? All right, question.
What is the definition of the end in the Bragg's law?
So this is different. This is not Bragg's law, right? This is the density. In Bragg's law?
Bragg's law is not density.
No. Yes, so I know. A lot of same stuff, right? But N in Bragg's law is the order of diffraction.
Oh, okay. Oh, yeah.
Don't worry about it. N here, so okay, so you remember about copper, right? Pure element. I keep talking about it, right? We just have copper. 4 atoms per cell. In reality, it's 4 formula units per cell because it's just a pure element. You have one element, so you have just 4 of them. But if you have an alloy of, let's say, alumina or something else, that's a ceramic, actually, alumina.
If it's 8, right? That's not an FCC or
No.
BCC or any
Well,
of
no,
that.
it is FCC. Okay.
It's not any of the
It is
compounds,
FCC,
right?
but you remember, or BCC, right? You remember interstitial sites, right, that I was talking about the iron? We have carbon and we have iron, right? Carbon can go into interstitial sites, right? That's because if we have iron alloy, or what do you call it? The alloy, right? We can have 4 or 8 carbon atoms and 4 iron atoms in one crystal structure.
And now it would be like 1 iron, 2.
And that's 4 formula units per cell.
Yeah, but this is 8 formula units per cell.
Per cell, yes.
And that's still FCC?
No, that's not FCC. That's something else.
This is the difference that
I don't know what the structure it is, right? In the question you have on PDF, it assumes rock salt. But here we do not assume anything.
we don't care about the structure.
No, we don't give a
Still
shit.
at
No,
And the
no.
structure will give us the end.
Oh
if
yeah,
we have
oh
it.
yeah,
Okay.
pretty much. All right, calm down, guys, calm down. Yes, question. Sorry, I'll come back to it. Yes. Yes.
You know you said R, right?
R magnesium, yes.
So it would just be 8 times 4 over pi 3.
That's right.
R.
Yes, that's right. That's right. All right. Question. Which one?
This type of question, is this the level that's going to come?
Oh, it's a very good level for the exam, yeah.
It's going to be 5 of this?
Is that going to be what?
There's going to be 5 questions of these, or 7?
What? Well, dude, I don't know.
Exams before, so was it this hard?
It's just one that could be like this. Yeah, I mean, it's not really hard, right? Is it? No, it's not. Practice it. It's not really hard. Question. Sorry, which one?
You know if they're going to put all the formulas, or like which ones do you have to know or memorize?
No, you're gonna have like a collection of all the formulas, and you will need to like know what they are, and you will need to pick like exactly what you need.
So there won't be like formulas that's not displayed.
Pretty much.
Small question. Is there like a formula sheet we could use while solving right now?
Is there a formula sheet we can use right now? I didn't make a formula sheet actually, but it's a good thing. I guess I should do it a year from now. Good stuff. Thank you.
Wait, he had version D.
Guys, come down, please. I need to listen to a question. Les, yes. Okay, one sec. I'm coming to you. All right, excuse me. All right, go ahead.
Yeah, can they ask the bigger atomic factors like 0. Unless it's close to 0.68, can they ask like, oh, is it BCC or FCC or something?
No. For ceramics, it's not gonna work. No, that's not gonna work. No. Question?
Yeah.
Go ahead.
Turning the calculation for the VX. So you use each atomic radii for
Yes.
the volume.
Yes.
So for the part where it's 4/3, you just do the atomic radiuses of each.
Yeah, pretty much. Yep. All right.
For VS, why do you multiply each?
By 8.
Yeah, why do you multiply 8 for every single?
Yes. I'll answer it right now. All right. The question is as such. I'll have to explain it again. Why on earth do we multiply by 8? The question is, why do we multiply by 8? Well, the answer to this question is because we don't have a pure element, copper, let's say. You remember how we computed, density of copper? Density of silver, you're lab number 1, right? Silver is just what? One element, isn't it, right? It's a pure element. So if we have some crystal structure, such as FCC, I believe silver is FCC, you know, we have one exact same radius of silver that just resides in your FCC crystal structure, right? What happens if I add to silver copper? You have now 2 elements in an alloy, right? Copper and silver. Copper will have, let's say, a smaller radius than silver, right? So that means that within this crystal structure, I need to have 4 atoms of copper and silver, assuming it's FCC crystal structure. Why? Before, when I always talked about N number, I always said how many atoms per unit cell it is. That's because we only worked with pure elements. So if we have an FCC crystal structure and we have an N number in FCC of copper, that's going to be just 4 elements per unit cell. And we only have one element, it's copper. So we just have 4 atoms per unit cell. Let's say we have an alloy of steel. I've been talking about this since the midterm. We have iron and we have carbon. We have iron carbide. Okay? So we have iron atom and carbon atom. If they are in FCC structure, and in fact, they could be in different structures depending on how you cool your metal. It's a different story. But if we assume it's FCC, it needs to be 4 atoms of iron and 4 atoms of carbon within one crystal structure. Just because of the way it is in alloys. Your N number is the amount of formula units per cell. It's the amount of atoms per element in the unit cell. Amount of atoms per unit cell. Okay? This is what I want you guys to remember. All right. And so the reason we have this nasty ceramic is for you guys to introduce that N is the formula units per cell, which means that in one crystal structure, whatever it is, I don't know what the structure it is. Okay, in the question on PDF, it assumes rock salt structure. Here, it doesn't assume anything. Okay, so we don't know what it is. BCC, FCC, HCP, could be anything. So, given that, we do know the N number. So we do know that we have 1 magnesium atom, 2 of iron atoms, and 4 of oxygen. So in total, you have 1, 2, 3, and plus 4, 7 atoms within one structure. Okay? All of them, they have different radii. They have different atomic weight. Okay? I don't know what they are. In one unit, so yeah, they all have one same crystal structure. Yes, it is. In the PDF file, it kind of says assume rock salt. If you don't see what kind of a structure it is, do not assume anything. Okay? I mean, who knows what it is? It could be anything, right? Until we figure it out and calculate it, okay? And we get our atomic packing factor 0.68. So we don't really know what crystal structure it is. Because there is, BCC is different, right? By everything, you mean like every element? Yes. Yes. It should be 2, yeah.
2 R
yes.
plus A is equal to root 3, right?
That is correct.
So if you solve for A, we just divide by root 3 and then that's it? And
yes.
Then, okay. And the other ones are still the same, right? Nothing's
Yep.
changed?
Oh, yeah, those are fine.
For this one, you just say FCC, so it's just 2 R's, right?
This one,
It says FCC structure right there, so I just assume it's 4 atoms and 2 R for unit cell edge line.
2R, 2 root 2 RC plus RA.
Oh, so every single one of them has a different.
Yeah, yeah.
Okay.
Yes, that's literally all you need to remember. Just 3 of them. Okay? All right, guys, we're going to move on from this chapter. Thank you. Two questions we solved. I selected these 2 questions to solve. They're pretty good questions. They pretty much cover everything you need to know for this chapter. For the theory portion, of course, you need to, look into the PDF file and ideally read the book. But here is basically, as I said, you have these 2 questions. You play with your parameters, ask a plotter or a GPU or something, give you the practice, you're good. Okay, these are very good questions to ask. And they're final exam level, all this stuff. All right, we're going to move on to polymers. All right. Any questions before we move on? Nope. All right, question. One question. All right.
Question 3.
Mm-hmm.
We're given absolutely nothing to be, like there's no A value here or something to be able to solve it.
Yeah, so when I send you the solution, right, you just kind of practice, you see. Like, I selected those questions from an old edition of Callister, some of them, not all of them. So, yeah, don't worry about it. You're going to be obviously given the questions, or back of the final exam sheet, right? All right, let's move on. Both screens. All right, now we're going to talk about polymers. So, all right, now we divert into a different topic of material science, polymers. By the way, those topics that you guys cover in MTL, they're very broad topics. Like in research, people can spend like a particular like their lives in a particular subsection of the polymer topic. A lot of people are working on, like, let's say, stress analysis of polymers. There are elastomers. Maybe you heard about that. It's a totally different topic. It has nonlinear behavior when it comes to stress analysis. So it's a pretty good research topic nowadays, elastomers and viscoelasticity, we also call it. It's pretty complicated. But what I'm just trying to say is that whatever you learn in MTL200, guys, is just a grain of sand. It's a very broad field of stuff. All right, polymer structures. So what are the polymers? Polymers are hydrocarbons. Okay, everything mainly that we use, most of it is made of polymers. Polymers could be strong, could be ductile. There's a lot of ways to play around. Now, they do have covalent bonds, so that's a very particular crystal structure that they have as polymers. Apart from ceramics, they could be ionic, could be covalent. All polymers are covalent bonds. Okay, we have carbon, we have hydrogen, we have oxygen, we have nitrogen. Those are the four elements that mainly the polymers are comprised of. Okay, and you do need to know the atomic weight of those basic elements. Okay, you better know, guys, because might not be given on the final exam. So carbon is 12, H is 1, oxygen is going to be 16, nitrogen is 12. Okay, make sure you remember that. Okay. All right. So we're going to talk about some families, types of polymers. So a very family is the graphene family. Yes, question. Four elements. Sure. Carbon is 12, right? Hydrogen is going to be 1, and oxygen is going to be 16. Nitrogen is going to be 14, I think. Double check that. All right. All right, paraffin family. So that, if you took a chemistry course in high school, definitely introduced with those elements. Methane, butene, and all that kind of stuff. We changed the anyway. All right, so we have weak hydrogen and van der Waals bonds between polymer molecules, and they could lower the melting. So a very final exam question to be asked on multiple choice side about polymers would be about so relating the length of your polymer to the melting temperature. Okay, atomic weight to melt or freezing temperature. Basically, the idea and the logic is as such: if you increase the length of your polymer, increase the amount of content. Okay, you increase of atomic weight of your polymer. And if you do so, you, at the end, require a higher melting temperature to melt your polymer. Okay? Just something I remember from previous final exam when I looked at the question could be like molecular weight of 15 and molecular weight of 20. Which alloy would have the larger temperature? Okay. Obviously, molecular weight, the higher temperature required to melt your polymer. Okay? So, that's something I have remembered. Okay, isomerism, same composition but different atomic arrangements. You can familiarize yourself with these things. Homopolymer, copolymers. I believe there was a question about copolymer on the final exam. I don't remember the question itself, but it was more about its definition. Okay, copolymer, 2 or more different repeat units. So just remember that. All right. All right. So be aware also of these types of polymers that also exist: alcohols, ethers, acids, aldehydes. So on the final exam, on the back of your sheet, you're going to have a page which is going to basically show you 5 different elements or 6. And one of the questions is going to require you to know what the chemical formula is. So you're going to on the final exam basically this, and you will just need to figure out how many carbons, how many oxygens, how many hydrogens are there, because from there you can compute your atomic weight, and from there you go. Okay, so that's something you should expect. Okay, yeah, nothing particularly super crazy you need to remember about ethers, acids, and all that stuff. You're going to be given all of this. Okay, molecular weight. Okay. So there's something I have to show you guys, very important. I'll have to spend some time on it. This chart, okay? So this is a distribution of molecular weight and, there are two things, average molecular weight and the weight average molecular weight, okay? So number and weight average, okay? In this distribution, what you need to remember, guys, is that the weight average of your polymer is going to be higher than the number average. This is essentially statistics, okay? You're going to learn statistics in second year. When it comes to polymers, the more you have, the more molecular weight you have. Basically, what this graph tells you is that the weight average is higher than the number average. Okay, so that could be one of the multiple choice as well. Just make sure you remember what I just said. Weight average is higher than the number average when it comes to polymers. Okay, so here I put a note that the first one divides the chain into a series of polymers. So it's basically a statistical measure. Okay, it's like a mean length essentially. A mean length of, let's say, I don't know, some structures of polymers, your aldehydes or your carbons and so on. Whereas the weight average is more biased towards the weight itself. Okay, so it's not a statistical measure. This is basically the mean. Okay, this is going to be your weight of a polymer, and they're different. Okay, so we're going to have one question, and that question was in the final exam, I think 2 years ago. I will show you how to solve it. Anyway, the first one divides the chain into a series of polymers and measures the portion of the polymer and it multiplies by the molecular weight, whereas the second one uses weight fractions multiplied by the molecular weight. So again, this is a statistical measure of the length, and this is more of a weight itself. Okay. Okay. Degree of polymerization. The length of the polymer can be determined based on the following equation. So how long the polymer is, we take a statistical measure of the polymer and divide it by m. Okay, and m is going to be our molar mass. It's essentially mass per mole. Okay, that we're going to use. I'll show you how to use this equation and how to solve the question. And you're going to have one of the questions guaranteed in the final exam about polymers. Okay, so polymers with a low chain will exist in a liquid state. So we're talking about less than 100 grams per mole. So they're very much mass dependent. Okay. In between, we have waxes, soft resins, we have elastomers, viscoelastomers, a whole bunch of stuff. So obviously, as you increase the length, the chain length of your polymer, you increase the atomic weight, okay, of your polymer. And of course, one of the questions could be also your length, atomic to mechanical properties of your polymer. So as you increase the molecular weight, it's a very much direct linear relationship, guys. Okay, so that's just all you need to remember. Very much common sense. If we increase the length, we're going to increase the mechanical properties, melting temperature. Okay. Shapes of polymers. Yes, I think there was one question about shapes of polymers a year ago. So in the final exam, familiar with rotational flexibility, Yes, types of stuff. Could also be one to push the double bonding of carbon. It is a rotationally rigid structure. So essentially, if you have a double bonding of carbon, it will not be kinked or twist anything. Okay. For example, benzene has a double bonded carbon. Okay, so that's going to be a structure. Very easy multiple choice question. Okay, so take a note of this. Question. Okay, just about physical characteristics, molecular weight, shape. So something about the shape as well is if you increase the randomness of your polymer, like there are a lot of kinks, twists, all of this kind of, that's going to also will require some energy input to melt. Okay, so the randomness of your position of the alloy, the geometry, does also require a higher melting temperature. Okay, so which is why I put a note here that the shape also affects the characteristics of your polymer. Different polymer, color changes, and so on. I've never seen a question about these when asked, but just in case, I have it over here. We have linear, branched polymers, cross-linked polymers, network polymers, so a whole bunch of different types of them. Okay, stereoisomerism. About this, but make sure you're familiar about it. The arrangements, tactic, do a tactic. Again, never submit a question about that, but just in case, make sure you're familiar that what are the different arrangements of your R-type links to your polymers, CH. So it could be something like oxygen, nitrogen, and something else. Okay, so basically, it's a combination of them. Okay, this is what's going to be determining the different configurations of polymers. Not complicated. Just remember this. And yeah, just another note: the conversion between these configurations is not possible by simple rotation. Okay, about a single chain bonds. Okay. So essentially, this reinforces properties of your polymers, which makes sense. The more stuff you add there, the more energy it requires to stick to concave and so on. So yeah, this chapter is okay. Blah blah blah. Yes, pretty good summary took from the textbook about all the different types of polymers and so on. You can guys take a look at it. I don't want to spend time on this. All right, let's do some practice questions because that's what matters at the end. Okay, this question, degree of polymerization. We're going to have one question. This. So degree of polymerization is basically given the fracture masses, basically what the mass is of your polymer. Okay, we're going to also have a question about it. Percent crystallinity, basically the ratio of your densities. Okay. So degree of crystallinity, blah blah blah. Density of the specimen, percent crystallinity, blah blah blah. Amorphous polymer, crystalline polymers. All right, let's do questions. That's going to be more useful. All right, let's bring this thing. All right, bring it in. First question. This question was from one of the final exams last year. I was able to take a. All right, question one. The question is as such. Calculate the number average molecular weight. So we're looking for a number average, a statistical measure of the weight of your polymer, of a random nitrile rubber polyacrylonitrile butadiene copolymer, in which the fraction of butadiene repeat units is 0.5. I assume concentration corresponds to polymerization. Okay. Here's the drill. You're given polymer. What you have to do is you have to go to your back of the final exam. There's going to be a page, as I said, of different polymer. So one of the polyacrylonitrile. Okay, so that's PAN in word. N. So you go to. Okay, that's going to be the shape. Okay, all you have to do is just you have to figure out what it is. It is C2H4. In a nutshell, it is H4. Polybutadiene. That's going to be structure. C double C, and then you have hydrogen atoms here, and here. So that's going to be your C4. Okay, that's it. That's all. That's when you go to your back of your. Figure this out. This is our butadiene. Okay? So the question is, we need to find the number average molecular weight. Okay, so in our given, okay, we have the degree of polymerization of 2000. We're given the fraction of the of butadiene as 0.5. I think it's 4,000. Is it 4,000? My bad. 4,000, 0.5. And okay, so if we know that the fraction of the butadiene, or polybutadiene, is 0.5, obviously the fraction of PAN is going to be 0.5 as well. Okay, because we just have these two elements together. So that's just 0.5. And we need to obtain molecular number average weight. Okay? So, all right. Let's now solve that. Very simple. That was one of the final exam questions. Pretty good. So, knowing that FPAN is equal to 0.5, which is the same as F butadiene, okay? We need to compute now. There's actually another nitrogen here, triple bonded. Forgot about this. So C2H4N. That's the chemical formula of this. So we have C2H4N and C4H6. Okay? Those are the two elements. So you're not given a single atomic weight. Okay, in fact, people were not given. So you need to remember your C, your H, and N. Okay? Question?
Wait, I'm sorry. How is the nitrogen bonded like that to the hydrogen?
No clue. I'm not a polymer guy. That's how it is. That's what I found in the back of the exam sheet like a year ago or so. Yeah, I don't know. I'm not a polymer guy. I have no clue how that stuff works. That's what it is, and that's what we need to know. Ignorance is bliss, okay? All right. C3, H3, C3, H3. Okay, no, it doesn't make sense to be it has to be carbon. It has to be carbon. I don't know why it has hydrogen here, but anyway, it has to be carbon. Then it makes sense to be triple bonded. Anyway, regardless of that, we have C3H3N. Whatever it is, you will be able to figure it out. You have your chemical formula. We have 3 times 12 grams per Somebody wanted to ask a question? No? All right. 3 times 12 plus 3 hydrogens, so 3 times 1 gram per mole, plus nitrogen, which is 14, so we have 14 grams per mole. Okay? To remember these things, they will not be given to you. Per mole. So then we have M of C4H6. So that's again 12 4 grams per mole. Don't forget your units. Plus times 1 gram per mole. Okay, so we're gonna have 54 grams per mole. Okay, very simple. Now that we know 2 molecular weights, we use the degree of polymerization. P equal to Mn divided by. So the question is, what is M? Okay, so in the PDF file, we discussed measure the degradation for polymer M. Okay, so what M essentially is of the fractions of your polymers that you have in your total structure. So it's FIMM. M is capital M. So we have a combination of 2 polymers. It's a PN. I forgot this already. And polybutadiene. 2 polymers combined together. We don't know how they were combined. We don't care. There are 2 polymers. So to find the total molar mass, this combined polymer, we have to take a fraction of this and a fraction of this. Add that together, get total molar mass for the polymer. Okay, common sense. So we have F, which is a fraction given as 0.5. Okay, it was given in the question. Could be any other number. So 0.5, plug it in. So 0.5 times the molar mass of polybutadiene plus 0.5 plus mass of poly, whatever it is, PAN. So that's how it is. We could have had a different number, 0.1, 0.4, 0.3. Again, it's a fraction, okay, of the total polymer. All right. So we multiply these two molar masses by a half. Okay, we add them together, and we're going to get a mass of 53.37. 53.37 grams per mole. So very simple. We can now our Mn is simply dP times M. Okay. So we have 4,000 divided by 53.37 grams per mole. You plug it in and you get your number. Okay? Very simple question. Okay, very good question. Was one of the final exam questions. So very easy question, 3 marks, I guess, but gotta show your work. Okay? Yes, do not mess basic stuff. Do not mess up on amount of carbons, amount of hydrogens. Okay, so very simple. Okay. Yes. C3H3N. So I initially made a mistake. Initially, this is what the polymer is. That's how it looks like. It has 3 carbons, 3 hydrogens, and 1 nitrogen. Okay? Yes. Excuse me, sir? M is number average molecular weight. Number average molecular weight. Sorry, 1 second. Yes.
What did the question ask for?
The question asked for the number average molecular weight, Mn. Okay.
You got 53.37, right? Are we gonna get P max if we don't use like the exact number? Like, you know, you got like, so like if you do 52 divided by 2, it's 0.5, right? If you get 37, that means you use like 14.011.
It's just the way it worked out, pretty much. Yeah, it just because the it was 0.5, right? And 0.5, they basically half and half of this.
Yeah, so half 2 would be like 0.5, so it would be a 0.5 number, right? We're gonna get P max.
No, that's going to be 25, and that's going to be what?
53 divided by
53 divided by 2, roughly. It's just numbers. It doesn't matter. Like, I mean, no. I mean, you got the idea, right? Okay, that's what matters. Numbers is whatever you calculate. Okay? Yes. Sorry, 1 second.
Okay.
Yes.
What other, like, is there a way we could have found what DP, FI or DP is without you giving it to us? Like what other types of ways can we alter this question?
Yes. Next question is about that. You're given a table. Yes.
Yeah, so for the butadiene, I don't know, I think you might have drew it wrong, because like, I don't know how to hydrogen.
It's 4 hydrogens.
Oh, okay. Like for the butadiene.
And I was lazy to draw hydrogen atoms.
Oh, okay, yeah.
Each hydrogen will have the hydrogen atoms except the 2 on the both ends.
Okay.
Again, it doesn't matter. For this question, it doesn't matter.
But it's going to show in the back.
Obviously,
like,
yes.
You just count it, right?
Yeah.
Okay, yeah.
Like, don't mess up the counting. That's the point.
Yeah, okay. Thank
All right, no worries. Question. Grams per mole.
So is degree of polymerization units?
Degree of, sorry, what?
Degree of polymerization is it units? Like 4,000? Would that be?
Does that have units?
Degree of polymerization does not have units because you divide grams per mole by the grams per mole.
So you just cancel. Okay. Thank you.
No worries. Yes. Perfect. All right. The next question. All right, guys. Sorry. Yes. You go ahead. Yes. Okay, I'm coming. All right. Degree of polymerization, and I heard about that, but what else? What does it mean? How long the polymer basically is. Basically, degree of polymerization, like the length of it. Yes.
This formula, right?
Yes, correct.
What is
Mn? So what is M? So M is basically your average molecular weight. By average, I mean it depends on the proportion of one polymer to another. You could have had like 50 of different polymers, and you would need to know in total the proportion of each one, right?
You just have to calculate like the. So this means like
This one is statistical measure of your polymer.
okay, and
The statistical measure of the weight of your polymer. Average molecular weight.
okay.
Yes. Yes. Okay. All good, I guess. You answered your question. If it's equal parts, you could have had 50 polymers. One would be 1% or, I don't know, whatever it is, 2% each, right?
And like I'm just confused about this symbol on the board. Like what is that?
Density? Or wait, is that density? What the heck is that?
It's like over there. It's like that weird like symbol with the pen. What does that mean?
F, it's F.
Oh, it's F.
It's F of BD. F is the percentage of it, the proportion.
So it's the proportion of the fraction, right?
The fraction of it, yes. Yes. One sec, sorry. Yes.
To determine, okay, if we're given this, to determine it, because it's copolymer, which means it's
So co means double, right?
yeah, double.
Yeah.
So then this one is the first half of it. Is that what
Yeah,
you're
yeah,
saying?
exactly.
And then
Yeah, yeah. That's the challenge of the question, yeah. Anyway. Go ahead.
On like the atomic mass, right? Like from C to C3, like 3 carbons to 2 carbons.
I'm coming.
Excuse me.
Yes.
I had a question.
Yes,
so
go ahead.
Since there's 60 multiple choice with 1 mark each, unlike the midterm, is all the calculation all of the last 5 questions, so all the other 60 questions will just be theory?
Yes, yes.
Okay.
There's going to be no questions to solve numerically on your multiple choice.
Hi.
Why do you swap like for a PAN? Why do you swap for like the formula to be C2 for H4N?
It should be C2H3N. Yes, that's right.
Oh, C3.
Yes, I made a mistake. You remember the guy asked about what the heck hydrogen is bonded to nitrogen? It should be carbon.
I couldn't hear him all the way.
I know, it's like fuck. Anyway,
Yeah, but-
I hope you get it. No worries, my pleasure. Question? No? Okay. Yes.
Is the final going to be mainly new stuff, or is it going to be like half and half?
I also have multiple choice. Again, every single year I have something new to add.
Yeah.
So you're pretty much okay to watch like previous years. Like the privilege of people who come here. I talk about some new stuff every time.
Yeah.
So pretty much. But like, yeah. That's what it is.
Thank you.
Next question. All right, next question. All right, that was the exam. That was the question on one of the final exams a couple of years ago. It was given a table in polymers. Okay, it was given a table, and the question was we had to calculate a couple of things. Okay, based on this table. So we were given fractions, okay, of the polymer and the weight fractions of the polymer and the molecular weights, okay, in ranges, okay. So how do we approach this question? Okay, I'm going to quickly talk about it. It's pretty simple. It's all based on the equations we just derived, okay. So pull it up on your laptop or phone as well, so I can bring up the board and you follow me, okay. So it's a very good question. It was also asked on one of the final exams. It's pretty good. All right, let me bring this up. Good. Go up. Alrighty. So, we just solved the question with two polymers. They're called copolymers. Co means two. What if you have like 50 polymers, 100 polymers? Okay. So this question is basically more of a complicated version of the previous one. So we're giving the ranges of M of our molecular masses. Okay. We have different ranges. We have our fractions. It could be X or it could be F. Okay. X or F, interchangeable. We're going to call them Fi. That's Mi. And we have our Wi. Okay. The weight fractions of those polymers. Okay. So the way we approach this question is by two things. We will need to create more columns. Okay. So we would need to find a couple of more things. So the question is first to find the number average molecular weight. So that's Mn. Okay, and the basic definition of this is the summation of Xi, Mi. Okay, so this is the equation of the average molecular weight, average molecular weight. So given the ranges from 10,000, let's say, to 20,000, what we need to do is we need to compute the average molecular mass per polymer. Okay, so we have M average, I, per polymer. So in the first row, it's going to be 15,000. Okay, next row is going to be 25,000. Okay, and so on. We can do basic addition and every stuff. Okay. Just divide by a factor of 2. So for every average molecular weight per polymer, now we need to compute per polymer the amount of fraction. Okay, statistically speaking. So we X the fraction, multiply by the average Mi that we just computed per polymer from the table. Okay? So first row was 10,000 to 20,000. The average Mi is 15,000. And how much of it is in the total of the polymer? 0.03. Okay? That was the number. So the next column we have to compute is Xi, Mi. Okay? And then what you do, you compute it for every row. So we're going to get something like 450 here. Then we're going to get 2,250. 5,250, and so on. And what you have to do at the end is you have to produce a summation of every single row in this column, okay, which is this equation. Okay, so you do that, and then you get the number. That's going to be your part A. Okay, so it's just a tedious question, not complicated. It was one of the final exam questions. Okay, so please be aware. So for example, we get the Mn value of about 49,800 grams per mole. Okay. Then we compute the same with the weight average. Okay, so MW. The equation of MW is the summation of Wi, Mi average. Okay, so we also have the values of Wi, 0.01, 0.04, 0.11, and so on. The exact same drill. We have Wi, Mi. You multiply that together, and then you produce summation. So we have MW is equal to 55,200 grams per mole. Okay? So that was the two parts, A and B. So just time consuming, nothing much. Pretty good solid question for the final exam. Part C, the number average degree of polymerization. Okay, so that's what we have to compute. So we're basically looking for the degree of polymerization. Okay. All right. So what is our degree of polymerization? That's the average number, okay, atomic weight divided by our M. Okay, that's going to be the average molar mass of the polymers. Okay. So what are we given in the question? I think we're given a particular polymer or something. Polytetrafluoroethylene. Okay? So you would need to go and look it up on the back of your final exam sheet. Okay? And we repeat the exact same procedure we did back in the previous question. Okay? was the second question about the two elements, PAN and butadiene. You repeat the exact same procedure. You're going to see an image of various positions of hydrogen and nitrogen and so on. You repeat this procedure, and you're going to find the average molar mass of this polymer. Okay, that's going to be something like 100.02 grams per mole. Okay, so the polymer was, again, like some stuff. Just look it up, get these calculations done, and very simple. You simply plug that M number into your degree of polymerization, and then you compute your dP. And the last part was to compute our polymerization, the weight average. Okay, so very simple. It's the same equation. Calculate your dP with respect to MW to M average molar mass. Okay, this and this, super easy. Final exam, you can guys do it. Okay, so those are the two basic questions. Any questions about this? Nope. Pretty straightforward. Okay, wonderful. Let's see if I have any other gifts for you. Question 5. Electrochemical promo is known to have the... Yes. Oh, I thought it was a question. Okay. One of the styrene. All right, let's solve this question. Pretty good one. Question number 5. All right, the question is as such. We have another copolymer. An alternating copolymer is known to have a number average molecular weight of 250,000 grams per mole. Okay, so this time we're given the number average, Mn, of 250,000 grams per mole. Then we're also given number average degree of polymerization. Okay, so we have dP of N, given the Mn and N. This is going to be, what's the value? 3,000? 3,420. Okay, beautiful. 3,420. Okay, and what do we need to compute? We need to find a fraction, okay, of a substance. We need to compute a fraction. So if one of the mers of the polymers is styrene, which ethylene, propylene, or tetrafluoroethylene and vinyl chloride is the other mer? So basically, we're given two polymers. Okay, we have one polymer the same way we had here, PAN, and the butadiene. We have one polymer, another polymer. Given the fact that it's in total of 100%, okay, we know what the M average is, the average molecular mass for these from this equation. The degree of polymerization is Mn divided by M bar. Okay, from M bar, your 250 by 3,420. Okay, you get some number. That's going to be something. Okay, now is ethylene. Okay, we can figure out what's going to be the chemical formula of it. Let's say it's some CXHY. Okay, so the other one is unknown. Okay, we're going to call it I don't know Y. Okay, so what we have to figure out is basically the percentage of that polymer, given the fact that we know our M bar, the average molar mass, and we have another polymer, okay, ethylene. Okay, that's what we have to figure out. And so let me write down the process. I'm going to save some time and not write down numbers. Wait a second. So this was the final exam question, I think, a long time ago. So we know that our M bar is going to half of the ethylene multiplied by the molar mass of the ethylene. Question? Yes.
It says one of the MERS is styrene, so how can we put ethylene?
Or styrene? Okay, well, whatever it is, it's some substance. Okay, I'm not plugging numbers in right now, so it doesn't matter. So we have some substance, we have or whatever it is, and another substance is Y. Okay, how do we approach this question? We have half of the ethylene or whatever it is multiplied by the molar mass of that substance, and you go back to your final exam sheet. You look C, 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 H, and H, whatever. You compute your molar of this. Okay. Add 1 minus F fraction of this substance. Okay. Multiplied by the molar mass of the substance that you're looking for. Okay. So in the question, you're going to be given the fraction of the one of this. So you're going to be given either the fraction of x or the fraction of y or the fraction of x. Okay? From here, you can figure out what's going to be the molar mass of the y substance. From the y substance, you go back into the final exam sheet, and let's say you're going to find you have some molar mass of let's say 50 grams per mole. It's the exact number. Okay? You will have to reverse engineer that number and figure out how many carbons could be there, how many nitrogens, and how many oxygens. Time-consuming question. That was one of the final exam questions. So on the back of the final exam sheet, like 5 substances. There's only 5 possible combinations that you might. You can compute right away for every substance the molar mass, and whichever the molar mass is the same as your calculated mass, then that is your y. Did you follow me, guys? Yes? Very simple question. It's just, again, one of the ways to reverse engineer, reiterate your variables to get a question. Okay? You were first. And at the bottom. So this is the fraction of this. I called it ethylene. It could be something else. Let's call it x. That's half of x times the molar mass of x plus f of y, which is 1 minus f of x, multiplied by m of y. Okay? And we need to figure out what is the. We don't know what the. Otherwise, we have one equation to f of x is equal to f of y is 1 minus f of x. It's a polymer. Yes, one of them. You know, it is one of them, and it's 100 times that. No, that's the only way to do it.
You have to give one, you have to give you one fraction, and you find the mass of that other substance, and you do other. Also, so for the exam, is it a structure where it's like an hour and a half? You have to do multiple choice, and then an hour and a half to do your.
Yes.
You'll take your stuff away. Okay. I have a question.
So, is it that? So you're given f of y, which is an unknown substance, and f of x is. That f of styrene times the molar mass of the structure.
That should be a
Yes, it's m of x.
Sorry, this is f of x, not f of y. This is all f of y. This is fx, 1 minus f of x.
But the thing is, like, you're only given one of the two.
Yeah, exactly.
So, how do you find the molar mass of y?
That's what we were looking for. Right. Okay, yes. No worries.
So you're given total molar mass. You have this molar mass, and you figure out this molar mass by just basically doing m total minus mx equals this. Then you find this, you have that, and then you're comparing it to the molar masses that you have, like that are given in the back, and that's how you decide what the MER is.
You can host. Question. Yes. Yes.
Then
Yeah, 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 exactly. It will be like, there's no way it's not going to be there unless you calculate it wrong.
Okay, so if it's like, right.
Which middle M? So that M is basically just an average molar mass of, it's a molar mass per element, like per element essentially. You just have carbon, you have a hydrogen, you have oxygen, and nitrogen. What is it? Just, huh?
So it's not average, it's just a molar mass.
It's an average because you have one substance and another substance. So molecular average per like a batch of elements, I'll put it this way. And whatever you have on top, M over N, is basically a length of like how many in total of polymers you have. Okay, it's like a lot of polymers. Yeah, average. Average. Very simple. DP given, you have Mn given. I want to find what kind of element it is. I don't know what the second polymer is. So it's basically a reverse engineering the previous question. Going in the
Diffraction thing, right? Is that given?
The other one. Yeah. About 1 hour. All right, guys. We have two more left. I want to bring up some questions from previous final exams. Question. No, this is like the big ceiling you can get. What I'm going over. The last what? Yeah. No, it's a total average. Final exam, yeah, final exam is not getting average. I'm not going to talk about it on camera later. But anyway, so, all right, let's begin to chapter 16 now. We're going to wrap this chapter up. I'm going to do a couple of practice questions. You do expect one of the questions final exam %. It always is there. All right, guys, please silence. I please. Thank you. So, composites. Basic stuff about composites. You have one element that is as a matrix, very useful, but on its own, it cannot perform well at all. You cannot apply it anywhere to any application. You have another element which cannot be applied to any application either, but it has a very high strength, super high strength. It's super brittle. Let's say it's some ceramic, something that is highly brittle, and however, it's so brittle that we cannot use it at all in the industry. So what do? We combine. Okay, so we start combining things. We can combine metals, polymers, ceramics, all together, use them, find the best optimum solution for a particular purpose. And composites play about that. A lot of civil engineering, a lot of aerospace engineering, mechanical composites. My particular research around this topic, it's a very broad topic. You combine different elements. For example, what I did, I combined the aluminum with the graphene type of carbon. Okay, so again, it's a metal plus that element together makes a composite. Okay, in order to bring the particular properties up, ductility, strength, and so on. All right, so I'm not going to spend much time on theory on this part. We're going to go into equations. That's going to be a pretty useful thing for the final exam. So, couple of things we need to remember on this chapter. So we have fiber reinforced composites. You've probably heard of DFR, carbon reinforced composite. You basically have a matrix, okay, and you have a substance, okay, that is being fused into that matrix, okay. A couple of assumptions we'll have to make in this course. When we apply any stress, it can be longitudinal stress or it could be lateral stress. By longitudinal, I mean you apply a tensile stress or compressive stress that goes into the direction of the cross-sectional area of your composite, okay? So if that is your cross-sectional area, let's say it's a circle or a square or some geometry, when you apply longitudinal stress, you either put it in tension or compression. Tension and compression. When we have a transverse stress, we usually call it a shear. Okay, it's a shear stress. So you start shearing the material perpendicular or at some angle to your cross-sectional area. Okay? So we have tensile, compressive, and shear stresses. Or what do we call them? Longitudinal and transverse, or yes, basically side stresses. Okay? So in this course, we have a couple of assumptions. When we apply the stress in longitudinal direction, we assume something called isostrain. So what is a strain? Strain is how much your material deforms. Okay, that's a deformation of your material. So strain is the initial length, a final length minus the initial length divided by initial length. Okay, that's how much of a percent of the strain you get, deformation, extension, essentially. Okay, so in this course, we assume that any longitudinal applied tensile or compressive stress is going to be an isostrain. What does it mean? Isostrain means you have this part of the matrix and this part of your fiber being fully bonded. There is no traction there. They don't move against each other. You assume that as soon as you pull on that material, you pull both of them. Okay? There is nothing that goes into a, like, let's say, perfect cohesion. Okay? There is nothing bonded. In reality, obviously, it's true. The carbon reinforced composites are probably the hardest to produce the analysis of strains because it's non-linear in its own nature. Okay, so now that is isostrain. So we assume if we pull this part, matrix, and the fiber move together and they extend together. If we have transverse shear, if we have the shear stress applied in this direction, we assume isostress in this course. Isostress means that the stress that the matrix experiences and the fiber experiences are the same, but the strains are going to be different. And the total strain is going to be the summation of the matrix and the fiber. Okay? So I repeat again, isostrain, trans. So there's an equation on the characteristic length. So the critical length is dependent on the fiber diameter and the ultimate tensile strength. So ultimate tensile strength is a mechanical property of your material, okay? So it basically on the stress strain curve, you have your yield point, Hooke's law. When you go to plastic deformation, that's the peak of the stress your material experiences, okay? That's the sigma F star. That is going to be your ultimate tensile strength, okay, of the material. And you can find this from the data sheets of the stress strain curve, okay? Okay, and the transfer shear. So we're going to have one of the questions on LC. This is not the question that is usually asked on the final exam because it's just very. You should be in all these elements to compute it. Really not that fun. Anyway, so a couple of ways we can create our substance, our thing. So we can have longitudinally positioned fibers in the matrix. Okay, so that means that in the transverse shear, there is absolutely to none load that can be applied. So it's super, super weak in the transverse direction, okay? But if you apply in the longitudinal direction, you can gain the most amount of performance there, okay? Now, the other ways would be obviously to mix it and make a whole bunch of variations, position your fibers in various directions, meaning that you have a compromise, and you have to have a compromise. You either put it in longitudinal or transverse, or you want to do it in both, but both are going to be lower, okay? So you have to do a trade-off analysis for this one. Equations, okay? So a couple of things. When we longitudinally load, okay, so those are the equations for longitudinal application. So I want you guys to follow me. Okay, I'm going to have to bring this one up. I want you to derive it. I want to derive it very quickly. All right. All right. All right. All right, so what is stress? Okay, you heard it many times, and you will hear when you take your stress analysis course in your second, third year, aerospace, mechanical, whatever you are, you're going to be learning about stress. What is stress? Sigma is equal to force over area. Okay, stress is essentially a pressure. It is an intensity load that is applied on the material. How do we apply the intensity? Apply a force over the cross-sectional area. I'm applying the intensity stress right on this board because the surface area of my palm is applying the pressure, and I vary the pressure based on my body, okay, the intensity of the load on the board. So I produce stress, okay? And it has to be force over area, okay? So sigma is the stress intensity, is the load intensity, okay? That's what it is. So since we have sigma as F times F over A, we also know that sigma is equal to E times epsilon. Okay, that's a Hooke's law. Okay, that's a Hooke's law. So when we go on the stress strain curve, we produce this. Okay, this is a very typical ductile material stress versus strain curve. This is stress. This is our strain. So in this region, we obey the Hooke's law. Okay, so we go linearly. So it's basically like a spring. If you ever do FEA, finite element analysis, and you want to model your element, your structure, you create an infinite amount of springs, okay? And that follow the Hooke's law, essentially. As soon as you depart from the linear region, from the so-called yield point, okay, that is our yield point, and the slope of that linear line is the Young's modulus. As soon as you depart from here, you go into plasticity, a non-linear behavior of the material that deforms under applied load. The main distinction between the plasticity and elasticity is that elasticity, when you elastically apply the stress on the material, and when you release the stress, the crystal structure goes back completely. But if you go into plasticity, this is what we call a permanent deformation. So as soon as you surpass the yield point, and you go and release the stress from here, your material is no longer the same as it was before. It was deformed permanently, okay? And there's a lot of science behind it, which you're going to learn later. But this is just the basics I want you guys to know. And so when we talk about ceramics, they're like this. Their yield point is super high, but they have no plastic deformation. Nothing. As soon as you apply your load and you go a little bit over it, fracture. Okay? But if you go and work with polymers, with metals, they have plasticity, the permanent deformation. Copper can deform into small diameter wires in order to create Ethernet cables, headphones, etc. That's because of this, the permanent deformation. But glasses cannot permanently deform, they fracture. Okay? So the fracture for metals is somewhere here. The fracture for ceramics is right here. Polymers could be one way or the other, it depends. Okay? Now that you know this theory, it's very helpful. Let's switch back to our composites chapter. So we have matrix and we have fiber. Fiber matrix. Basically, in the longitudinal direction, we assume isostrain. So E total is equal to ME matrix is equal to E fiber, epsilon fiber. Okay? Isostrain. Okay? Let me pull this up so people can see stuff. All right. All right, when you apply the longitudinal load, you apply the force. Okay, you apply the force. Force over area creates the stress. So the total load, F total, is going to be the F of the matrix plus the F of your fiber. Right? We know that the sigma is F over A. So F is equal to sigma times area. So the F total, or rather the sigma total, okay, the total stress essentially applied on the material is going to be our stress times area, because it's a force. Stress times area total is equal to sigma m AM plus sigma F AF. Okay? Now the next trick that is used in this chapter, okay, the reason I'm deriving these equations is because on the final exam sheet, you're going to have a whole bunch of these equations. If you don't know what the parameters are, you don't know what equations to use, you're not going to be able to solve a question. So I want you guys to be familiar with this entire process of derivation. Let's divide by area total. So we have area divided by total area, total area, total area. We get the total stress of the composite is sigma m times AM over AT time plus sigma F AF over AT. Okay? That is one step. Then we have to define something called volumetric ratio. Okay? So basically what we define in this chapter is that basically it's a fraction. Okay? We know the total area. So the total area is this. Knowing this area, we can find the matrix. Or knowing the matrix, we can find fiber. So we basically say that AM, let's say, over AT is going to be called the volumetric ratio of matrix. And volumetric ratio of fiber is A fiber over A total, or simply 1 minus VM. Okay, those are the two things. And they're very useful. We're going to be using them. So the sigma total is essentially sigma M VM plus sigma F VF, where sigma is the stress, V is the volumetric ratio of your area. Okay? And from there on the PDF file, basically you see the derivation using now this equation, the Hooke's law. Because we assume in this chapter we're only linearly going. We don't go into plasticity. So we only stay in this region in this chapter. Hooke's law. We fully ignore this. Okay, we're only here in the linear chapter. So we take that equation, the Hooke's law, which is sigma equal to epsilon times Young's modulus. Now we have two more parameters. We have Young's. So now we plug this all here, and we can play around. We can plug this in. We can figure out what's going to be our total Young's modulus. We also have to keep, in fact, to keep in mind the fact that total strain is, again, equal. It's an isostrain condition. Okay, so that's how it is. Okay. All right. All right, so as you can see in this chapter, you can have a whole variety of possible questions you can be asked on the midterm, right? We have too many variables, a lot of variables. We have Young's modulus, we have strain, we have stress, we have areas. So this chapter will take a lot of your time during the practice because of all possible combinations if you wish to go down that route. Let's project stuff. All right, so I just derived these parts, okay? So this is what you have. You have a total force. We know what the force is based on stress. Now we go into the volumetric ratio. We know the isostrain condition. We go here and we can find our Young's modulus. So it's simply the Young's modulus of the matrix plus times its proportion times plus the fiber. From here you can do all these shenanigans. Okay? Very simple. You can derive all of this on your own. So equations. All right, but that's longitudinal application of stress. There is also transverse loading. Okay, so in the transverse loading, there's another approach. So we assume that not the strain is equal, but the stress is equal. So this entire derivation will have to go from another angle. Here we assume that the equal, saying that the alone, the strain, the total strain, in the transverse direction will have to be the strain of the matrix times the volume of plus the fiber. Okay? So the exact same logic, except you use the Hooke's law in order to prove that. And you already know what the Hooke's law is. Okay? And from you can figure out again interpreted the Young's modulus. Okay? So I spend time to derive it because this is basically just a derivation from these equations. And again, for this chapter, two main equations, Hooke's law and the stress, force over area. And you have to know two conditions, isostrain, transverse shear, isostress. If you know these four equations, you did any equation of any sheets on the back of your final exam. You can derive it on your own. These are just the four things you have to know about this chapter. That's all you need to know. Okay? Question? Isostrain, isostress, stress area, stress, epsilon times Young's modulus as your Hooke's law. These are the main four things that got Hooke's law, stress as force over area, a basic definition of stress. Now the conditions for longitudinal, isostrain, for transverse, isostress. That is it. And you don't need even any other questions. You just know that it's going to be a linear addition, and that's how you figure it out. Super simple. In the book, it's all over the place. It's just equation, text. Very simple chapter. Just governed on 4 principles and nothing more. All right, a couple of more equations. Following this, we can figure out the longitudinal tensile strength. That's going to be given in your equation sheet. Okay. I want you to be familiar with these equations. Okay. So that uses the UTS, the ultimate tensile strength. Okay. So these equations are going to be provided in the exam sheet. Okay. This one allows you to correlate the stress to the characteristic length. Okay. This equation is almost never used on final exams, but it might be given, and if it is given, then super simple. Just plug in the variables in. I didn't see it at all on this middle equation, as well as. But anyway, just in case, I have some practice questions in as well. Anyway. Okay, so basically these equations are for, again, conditions. We just had 2 perfect conditions, longitudinal applied stress and transverse applied stress on that are longitudinally located. Now, what happens if we have a discontinuous and aligned fiber composite? That's the equation. And discontinuous and aligned fiber composite for longitudinal stress. Again, these are just the equations that are going to be given and figure out what the numbers in, okay? And as well as this. All right, let's do some questions, problem solving. That one's going to be fun. All right. All right. All right. This was one of the exam questions a couple of years ago. I was able to memorize it and replicate. So, you're given the following. A continuous and aligned fiber, okay? So again, as I said, in this course, we have a couple of things. We have isostrain, isostress, two equations. These equations apply for longitudinally load, aligned, longitudinal and transverse load aligned fibers in your matrix. There could be also misaligned. Okay, those were the 3 equations you saw at the end. You have to read the question carefully. If it says longitudinally applied, you apply the longitudinal equations. If it says transverse load, you apply transverse equations. If it says aligned fibers, you apply these aforementioned 2 equations to that particular composite. If you have a misaligned, you all of the above. It's not going to so you go into the final sheet equation and you find the equation of the misaligned discontinuous fibers. Okay? You got to read the question. That is why I encourage you to write down givens, because the given does imply that you're going to figure out what the question is talking about. All right. So what are we given? In this question, we have a table. We're given 2 components, matrix and the fiber. So the aramid fiber has a modulus of elasticity and the tensile strength. Okay? So we're given that we have the E of the fiber, we have the 6 sigma M max, we have the sigma F max, and we also have E of M. Okay, we have these numbers. So the maximum stress of the fiber will be 65 megapascals. Okay, we have sigma fiber max. This one should be 350, 3600. That one is 65. Okay, megapascals and megapascals. Okay, the Young's modulus EF is from the table is 131, and that one is 2.4. Just 1 second. 131, 2.4. That's going to be gigapascals, I presume. All right. Your fiber will have to have higher stress and higher Young's modulus all the time. Do not mess up the numbers. If you see that your matrix has a higher Young's modulus, it's wrong, okay? And if you do your calculations and you figure out that your Young's modulus of matrix is higher than Young's modulus of fiber, that's wrong. Your matrix will always be lower in mechanical properties than fiber. Just a disclaimer. Yes, somebody had a question? Okay, good. All right, let's read the question. So, a couple of things were given. We have a volumetric percentage given. We have a volumetric percentage of the fiber. V fiber is 0.25. So we know that the area, we don't know the number, but we know that it's 25% of the fiber and 75% of matrix. All right, we also have the total cross-sectional area. So we can actually figure out where our areas are. Total area 320 millimeters squared. We're also given a total amount of 44,500 newtons. Okay? So we have a lot of information. A lot of information and a lot of equations. All right, the first part is we need to figure out, calculate the modulus of elasticity, Young's modulus, of this in the longitude. That's part A. We have to figure out our E. And it has to be E total, comma, longitude L. Okay? Then we need to find B. B is going to be the stress. So F to 450. Now we the total longitudinal stress. That's sigma CL. Then we need to find out actual loads carried by both fiber and matrix. Okay, first we need to find the ratio of forces, and then we need to find the forces. So first we need to find of fiber over F of M. Then we need to find the F itself and F of M itself. And then part E is we have to find sigma F, sigma M, and then part F is we have to find the strain, total strain. Since it's longitudinal, what kind of condition we have? Isostrain. So it's going to be isostrain. All right. So that means that after you find all of this, you can find either fiber strain or matrix strain. That's going to be the same as your total strain. All right. A lot of things to also, the problem was this question. It was in the final exam. If you get one of the answers wrong, the next question uses the previous answer. Okay? So you need numbers correct in order to get solution. Okay? So first question is we need to find our Young's modulus. Okay? So I'm going to move on over here. So step number 1, or part A, we need to find Young's modulus. From before, and it's going to be given in your equation sheet, you basically take it and plug it in. We have ECL is equal to E of matrix times volume of matrix plus E of fiber times volume of fiber. We have everything, don't we? We do have EF, we do have EM, we do have VF, we can find VM. You plug in your numbers, and you find that your ECL is 34.55 gigapascals. Okay? That's your E. That one is very simple. That's part A. Part B, you need to find the stress. Okay? You need to find the stress of your longitudinally applied load, tensile load. We also have another parameter that was that I didn't mention. We have a sigma fail. That one was the thing that confused people on the final exam. Yes?
Could we also just do force total equal force CL equals area times, sorry,
Yeah, but it's just more work. You're already given the volumetric ratio. Why do you need to care about area? Care about area when you're looking for stress. Here we're not looking for stress, right? All right. So we also given the question, the stress in the polycarbonate matrix when they aramid fibers first is 45 megapascals. This is the thing that matrix when the fiber fails is 45 megapascals. Okay, so how the heck do you deal with this parameter? You cannot just ignore it, okay? Question. Let's say we have a fiber. Let's say we pull so hard that the fiber fails. And we're going to have a stress for the matrix remaining as 45 megapascals, okay? So, in order to calculate further longitudinal stress, you may not use the maximum stress of the matrix. You have to use the fail stress of the matrix. Because when the fiber fails, this is what it's going to experience, okay? We need to find not the total sigma of the longitudinally applied stress. We need to find just the stress, okay? It's being applied through this condition. This is a very important condition. This is what people ignored in the final exam, and they got all the answers wrong, okay? The sigma fail, okay? If you're given in the question something about fail of matrix, you need to incorporate this into all your equations, because this is your limiting reagent in a way. This is your limiting factor, not this. This is just the mechanical property of your matrix, but it doesn't mean anything because when the fiber fails, this is what we're going to experience, unless you're asked about the maximum total longitudinal stress. And you're not. So we have to use sigma m fail in order to compute the stress that is being imposed on the fiber in the longitudinal direction. So sigma CL is equal to sigma matrix fail. So the condition of the matrix after the fiber fails multiplied by the volumetric rate of volumetric percentage of your matrix plus sigma of breaks. Matrix is the remaining thing that is left in your composite times VF. You plug in the numbers, everything is given. So the trick in this question in part B was just you have to know which one to plug in and not ignore what is needed. So you plug this in, you get the number of 933.75 megapascals. Okay? If you're not given in the question the failure stress, then you're good. You just simply compute the maximum total stress. If you're given the failure stress, this is what you use for the matrix. Very simple. All right, part C. For part C, we need to compute the ratio of forces. Okay, we need to compute the ratio of forces of the fiber to matrix. Okay, how do we compute the ratio of forces? Well, that's how we derive the equations. We know that the force is stress times area, right? So we also know that stress is Young's modulus times epsilon. Those are the two main equations that govern this chapter. Hooke's law and the basic stress intensity. Okay? From here, we can correlate the force and the Young's modulus from these two equations because this is the stress. They're equal. Okay? So when we plug it in, we get that F is equal to epsilon E times A. Okay? This is the equation of force. Reiterated in terms of the Hooke's law. Okay? After, we could compute areas if we want, but we don't need to. We have ratios. So we know that our volumetric ratio of the matrix is AM over A total. So that means that AM is equal to VM times AT. Total area multiplied by the volumetric ratio. AM over AT. So AM is VM times AT. We can say the same about VF. It's AF over A total equal to AF is equal to VF multiplied by AT. Two things here, force and this. Okay? Let me erase now those two parts. Okay, now we have to plug it all in. So, we derived two things, just to recap. From the force, we know the stress and area. From the stress, from the Hooke's law, we can plug it back into stress. We get this equation for force. So we know that force of fiber over force of matrix is equal to this stuff, so epsilon of fiber multiplied by Young's modulus of fiber multiplied by the area of fiber divided by Young's or the strain of matrix multiplied by the Young's modulus of matrix multiplied by the area of matrix. All right, now we have the areas in terms of the volumetric. So now we can plug it in, areas. So we know that AF is simply VF times A total, and AM is VM A total. Basically, this step was unnecessary if you do see that AM over AF is the same as VM over VF. Okay? This is what it is. The ratios of areas is the same as the ratios of your volumetric ratios. Percentages. Anyway, so we plug this in. Also, isostrain. right? Longitudinally loaded fiber. These things cancel out. Now, when you plug this in, you have total area, and the total area cancel out. So you're left with Young's modulus of fiber multiplied by the VF over Young's modulus of matrix multiplied by the VM. Very simple, okay? This is the ratio. We get 0. What do we get? No, 18.19, okay? 18.2, roughly. That's the ratio of forces of the matrix to the fiber. So, does this make sense? You need to ask yourself on the final. Yes, it does, because when we reiterate that, we know that F of F is going to be 18.2 times more than the matrix force. 18.2 times Fm. Does this make sense? Yes, it does, because the fiber, again, has always been withstanding more force, more load than the matrix. If you have it the other way around, check it out. You got it wrong. Has to be fiber greater than Fm, always. FF greater than Fm, not the other way around. So that is good. That is correct. Now we're moving on. Okay, now, if you got these parts correct, the rest is super chill. You just simply from here, you know your total force of 44,500. Where the heck is it? Over here. So you just simply compute over here. Let's do it. Where's my stuff? So I'm going to keep it here. We're going to return there. All right. So now we need to find G, forces. So force of, we know that FF plus FM is equal to F total. And we're given the F total, 44,500 newtons. Do we know the ratio? Yes, we do. 18.12. F of F over F of M is equal to 18.2. What is this shit? It's a system of equations, okay? Very simple. So you just simply plug in F of M to M, M and F, and you can figure it out, okay? So now you can fully get your F of F and F of M. Super simple. Force of fiber is going to be 42,191 newtons, and force of matrix is 2,319 newtons. Okay? Does it make sense? Yes. Matrix is lower than fiber. If you get it the other way around, you have to stop here. Okay? You have to stop and spend time and go back. If you keep going, it's going to be all wrong. Okay? Has to be the other way around. So, okay, from now on, we just need to compute the stresses. Okay, do we know the total area? We do. So, total area is known. What is the area of fiber? V of F times A total. So A of F, what was the fraction? Volumetric fraction. 50%, no. 30, 25%. So 25% of the 320 millimeters squared. This is going to be 80 millimeters squared. Okay. And then we have M. That's going to be 75% of the total area. So that's going to be 240 millimeters squared. Beautiful. Chilling. Simply plug into stress equation. What is the stress equation? Sigma is force over area. So sigma of fiber is sigma of F of matrix divided by the area of matrix. Stress of the fiber experienced in this condition given the failure of the matrix. Okay? So we plug in 2,319 divided by 240 millimeters. Okay? So also one trick for you in terms of units. One trick, it's very useful. When you divide newtons by millimeters squared, you automatically get megapascal. Why? Because millimeter is 10 to the power of -3. Square, 10 to the power of -6. Bring this up, 10 to the power 6 is megapascal, or mega. And you have Newton over meter, which is a definition of your stress. Newton over meter. you get megapascal. So you don't need to do any unit conversions, okay? So Newton over millimeter squared is automatically megapascals. All right. So for sigma and for sigma, we also get some number, whatever that number is. And again, from here we need to compute strain. What do? Hooke's law. Where is that Hooke's law? Over here. Now, do we know stress? We do. Do we know Young's modulus? We do. Now all we need to do is to find strain. And all isostrain. So we just need one of them, one of the stresses. E is sigma over E. That is it. Plug in one of them and you're done. Okay, question. Oh yeah, that was the exam question. Yeah. Okay, but like, to be honest, is it difficult, this question? It's difficult. Okay, it's difficult. Why is it difficult? Too long. Yes, it is too long. But is it intellectually difficult? Yes, if you miss something, yes, yes. But like, you have like 50 million of small steps that you must be competent in. And if you're not, then a total picture is all ruined, right? Basically, yeah. Yes. Oh, yeah. Yeah. No, no.
The stress on the fibers equal by the area of the matrix. Would it not be the one?
Sorry, can you repeat that? Why is the force?
Why is this, like, you did the equation there. Is the force over area?
Yes, yes, yes. I probably made a mistake. So it has to be fiber, 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 matrix, 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 matrix. Yes, you go ahead. Sorry. Good question. I would. You're gonna have out of 7 the long problem, probably 2 or 3 that are midterm. For multiple choice, really hard. I'm not. Sorry about that. It probably will be a huge mix. Epsilon is a strain, yes. Yeah.
Okay, and what's strain and stress?
Well, stress is the intensity load, and strain is the extent of your element, of your material. Like literally, it's a unit less.
Okay. Oh, because.
Where's the Hooke's? Megapascal, right? But also another definition of strain is this. Initial. I have this, I pull in my material. What is that thing? It's the percentage of your total extension.
Strain.
Correct.
Strain, right? Or is that?
What do you mean?
I'm confused which one's strain, which one's stress. I'm looking at that.
Well, you apply strain and strain. So this is longitudinal direction when you because you induce the strain based on the stress. Okay. It's a Hooke's law, right?
Yeah.
So if you apply the stress, it's gonna elongate. It's gonna strain.
Okay, and
And E is the resistance of the material.
yeah, and then your epsilon is equal in for all transverse. Or sorry, the
Yes, isostrain, because it's a longitudinal direction.
Or because they're also all connected. Like,
You assume it's perfectly bonded.
Yeah, that's why we assume. What about transverse?
Doesn't apply for transfers.
Or do you think we're going to get asked the transverse question?
Yeah, we have a transfers coming up.
Okay, sounds good.
Yes.
Thank you.
No worries. All right. That's what you have to practice, okay? Yes. I guess I will come. Un momento, excuse me. All right. Please go ahead. Isostress for transfers, Hooke's law, and the regular stress intensity equations. Okay?
Thank you.
Wonderful. Yes.
To talk about the strain experience.
Yeah. I just said that. It's basically you use Hooke's law, and you pick either matrix or fiber.
Oh, you just use.
Yeah, because it's isostrain condition. It's in longitudinal direction, so it has to be isostrain.
So you can be
Either or, and total is going to be the same because you assume they're bonded together. Yes. Yes, yes. That's a transfer shear. That's a different question. Yes, sir. Yes.
Sorry, how did you calculate the VM and the VF
For what, sorry? For
for part A, because you said it's an EM and EF, which were given. But
oh, that equation, it's going to be given in your equation sheet. But if you want to derive it, you use the Hooke's law and a regular stress equation.
no, I mean like, how do we find the values for VM and EF?
Oh, VM is going to be, one of them is going to be given always.
And then you can just find it through the...
Yeah, of course. Well, it's at 100% in total.
Okay.
So if you have a 25% of your fiber, what's going to be the amount of matrix? 75. Okay. Yeah, but if you're going to be given the rest to find one of them. Again, you just play around with variables. Yes. I didn't work on the formula sheet, to be honest, but I had a comment from this gentleman. I will work on it next year. Which one?
You don't have the formula sheet.
You don't have a formula sheet, but you can make one. That's going to be part of your process of studying, right? Okay, question.
Are the questions going to be like equal amount for all the chapters, or like mainly focused on aspect midterm?
I cannot say. I cannot speculate. Really hard. Like 1 year it's one second year it's the other. It's just like imbalanced, kind of, like, you know. But again, like as I said at the beginning, one depends on the other. You cannot use, you need to have knowledge of the crystal structures to answer the questions about ceramics, right? Pretty much, yes.
So we're almost done, right? Like we're on the last...
Yeah, last chapter and we're done.
Yeah, so after that, do you do like the actual
Of course,
problems?
yeah, of course, yes. Multiple choice, yes.
Is chapter 13 covered on the final?
Ravi never taught this chapter. I don't know why people are asking me about chapter 13.
The professor Shajari.
She doesn't know what she's doing. There's no chapter 13.
Okay.
No.
Because she taught it apparently. That's why I'm wondering.
No, there's no chapter 13. I don't know what she's doing, but there is no chapter 13. 100%.
Okay.
I also wanted to ask, is it enough to just study your...
Gonna be satisfied?
Maybe.
I don't... Yeah. You have this. You find the balance between both. If you want to get B+, you just do this. If you want to get A+, you do both. So this 4-year statistics, I can guarantee you. Literally. All right, team. Let's move on. Oh God. All right.
You think this
If you want to get A+, you have to do both. Yes. There's going to be 7 calculation questions and 60 theory questions.
Like the multiple choice?
Oh, sorry. There's going to be no calculation and theory questions on multiple choice. So all multiple choice.
And long answers, like
Long answer will have to be this type of answer. No explanation? No. Problem solving, basically. No worries.
How would you say is the difficulty of the multiple choice?
Difficult multiple. Okay, imagine you didn't know the questions for your midterm. That would be the difficulty. All right. Well, here we go.
I don't know this.
Well, the midterm was recycled. It wasn't recycled. Would it be difficult? Yes. Yeah, so that's going to be the complexity of your final exam. How is this explained? That's the way it is. All right. All right, team. Last question for this chapter, and we're moving on. I want to finish corrosion quickly and do 2 questions from the midterm chapters, which I guarantee are going to be on your final exam. The one about diffusion and the one about... There's something interesting I have for you to show as well. After we're done, I'm going to be done with the recording, and we're going to go over some multiple choice questions. Same drill as always. We're getting by 9, okay? So that'll be the hard cutoff. All right. Last question for, do you want me to do the transfer shear or okay? Transfer shear? No? Okay, it's very simple. You literally just plug in equation numbers, okay? Some time. Are you okay to skip? Yes. Okay, perfect, thank you. We're skipping transfer shear. Transfer shear, basically, you do this, except it's just easier because all equations are given. You don't need to derive anything. So yeah, question, you will practice it. I'm going to send solutions to all questions, obviously. So all good. All right. Well-beloved corrosion. Let's begin. How's the recording? All good? Yeah. Nice. Perfect. Thank you. All right, team. Let's move on. Last chapter. Okay, we're finally here. Let's do it. Corrosion. So all of you had your corrosion experiment for MTL labs. Wonderful. Okay, so what is corrosion? You have essentially electrochemical process. You have electrons leaving and electrons being deposited on a surface of a material. Okay? We have cathodic reaction, we have anodic reaction. When you talk about corrosion, you have to create a couple. It has to be cathodic, anodic couple. One cannot exist without the other. It has to be electrons leaving and electrons depositing somewhere. Only in this way you can create electrochemical process. The force that drives the electrochemical process as such is called the electromotive force, EMF. Electromotive force is a function of the substance of your medium where you perform your electrochemical process. And it is also a function of substances, obviously, the two elements that are being in couple. And the third one is whether there are any external factors, pressure, temperature, any induced current. If you supply more current through the medium, you will accelerate the process. This is called polarization. Okay? Polarization is when you introduce an external source in order to speed up the electrochemical force, electromechanical force, EMF, in the couple of your corrosion. Okay? So, oxidation implies the electrons are leaving the material. Okay? And a reduction is when you're getting electrons coming into the substance, okay, in order to become passive. With the passive, it means that you have all your electron orbital shells being filled and you produce some physical process, whether it's gas, like hydrogen bubbling, when electrons are coming and coming with the hydrogen ions, they become hydrogen gas bubbling, but that depends on your atmospheric pressure and temperature, okay? So we have reactions. We have, in a nutshell, corrosion is electrochemical transfer of electrons, basically what I just talked about in a nutshell. Okay, we have oxidation and reduction. So I just explained all of this. Okay, EMF series. There are two things that I want you guys to be aware of in corrosion. Corrosion is a huge field of materials science. Huge, humongous. People do research in that for years. There are two things that you need to be aware of, EMF and galvanic series. Does anybody know the difference between EMF and galvanic series? What is the difference? You probably heard about both, EMF or galvanic, right? Have you? No. Damn. Cooked. Just kidding. All right, what is the difference? EMF. So EMF is basically the table that you're going to be using in MTL200 is basically this table. Okay? This is the electromotive force table that basically says that, hey, we have a standard electrode potential being measured against the hydrogen. Hydrogen in this configuration is 0. It is 0 volts. Where is hydrogen? Right here. Wait, it's not 0 here. Okay, yeah, it's 0 over here. Hydrogen. So with respect to hydrogen as a datum point, we produce all our measurements, okay, for these series of electromotive forces. Another important point is the fact that they're called standard electrode potentials. There are two reasons why they're standard. First reason is because they're pure elements. You do not see any alloys. You do not see any ceramics here. Ceramics. But you do not have magnesium, copper, sulfur alloy. No, you have magnesium, you have copper, and aluminum. Pure elements. That is why it is EMF, because it's standard electrode potential for magnesium, for iron, chromium, and so on. Now, galvanic series are the series that are being produced empirically, numerically, for alloys and elements. And they're done under various environmental conditions. It could be pressure raised to 5 ambient pressures for some reason, temperature of 100 Celsius. Obviously, whatever is here is going to be fully changed because you have not just the pure element, you have the alloy. You don't just have a standard electron potential, which is, by the way, in this table measured only at 1 atmospheric pressure and 1 degree Celsius, which is 73 Kelvin, for this only table. So this is not for the industry. This is trash. So if we want galvanic series, like ship, right? We have steel alloys being on the parts of the ship, and they're constantly being submerged into the seawater, a high amount of salt, right? Salinity. So you cannot use this because steel is an alloy. You have to go and search for empirical values and find the data, okay? Because temperatures could be variable, could be 2 degrees, could be not 25, right? All right. So I hope we were clear on that. Passivity. So what is passivity? This is just another way of saying that, hey, EMF is just a really perfect way of representing the corrosion. Passivity essentially implies that, let's say aluminum. We all know what aluminum is. If you look on this table and you couple your aluminum, let's say with some cobalt, right? Your aluminum is going to be, sorry, oxidizing. Let me get a sip of water. All right, so your aluminum is going to be oxidizing. Now, on this stage, it's going to be happening. But it's not true in reality. We know that when aluminum is in contact with oxygen, it's going to create aluminum oxide, aluminum 2O3. That is essentially a passive layer that is being naturally produced by aluminum. So when you have aluminum just being like on the floor, being exposed to oxygen, you're going to have this passivation layer being produced, which means that if you do to couple it with cobalt, performs on the table here because it has a passivation layer. Okay? Aluminum 2O3. All right, corrosion rate, the CPR, corrosion penetration rate. You use this equation in your experiment, number 5 in your lab for MTL200. Basically, what you do is you measure the weight before, the weight after. You put your chemicals through, and you'll observe how much of a weight got reduced or deposited on your material. Super simple. Polarization. This is what I mentioned. We have standards of the voltage being produced between the two elements. So if you want to speed up the process, you need to apply some current. Okay? You need to apply current in order to speed up the process. That's all you need to know about polarization. If you want to learn more, go to the textbook. Okay? There are 2 types of polarizations: activation and concentration. I'm not going to dive into it right now. You can read a book, and there are some equations here, of course. All right, that was quick. We're going to do some practice questions. That's kind of all you need to know. All right. So all right, let's bring the shields up. All right, we're going to do question number 3 from there. All right, the equation or the question is as such. So we have electrochemical cell is constructed such that on one side is a pure nickel electrode, pure nickel. It is in contact with a solution containing nickel 2+. We have some ions being produced at a concentration of something. The other cell half consists of the pure iron electrode that is immersed in a solution with the ions, having the concentration of 0.1 molars. Temperature will the potential between the two electrodes be 0.14 volts. So, obviously we already know, we need to write down what is there. So, as I said at the beginning, if you want to have a chemical process, you need to create a couple. And we do have that couple. We have nickel being produced, nickel 2+. Okay? We have that. We have the concentration, and the concentration is denoted by these square brackets. Okay, that's the concentration of nickel 2+. As ion concentration, that's what it is. Otherwise, it would be mass. 3 millimolars. So 10 power 3 molars. Then we have iron as another pure element, and I want to put an emphasis pure. We need to series as pretty much for this course. So Fe 2+, and we know the concentration of Fe 2+ is 0.1, I think. Yes, 0.1 molars. The voltage that we expect is 0.14 volts. So in your lab experiment, okay, if you were to do this, what do you call it, experiment, you would put nickel, you would put iron, you would measure this, okay, on your voltage regulator or the thing there. So here, we need to find the temperature. What is our T? Okay, the temperature in almost every chapter of this course is in Kelvin, okay? You do need to know the conversion. This will not be given to you. It's 273.4 Kelvin. Okay, that's the conversion between Celsius to Kelvin. So if it's 25 Celsius, that's going to be 25 plus 2 plus 2 plus 3.15. That's what you do. So we need to find the temperature. Okay, so we need to create now a couple. Okay, we need to you are going to be given a table. Okay, so I'm going to put down one of the things. You will be given the EMF series table. This table will be given to you. So from this table, we need to figure out which one is anodic, which one is cathodic reaction. We so far do not know. Okay, we need which one is below, essentially, more anodic, which one is more cathodic. So what do? You look it up. We come here and we see that iron will have the standard electric potential with respect to hydrogen. Okay, so what they did, they put hydrogen and iron. Then what they did, they put hydrogen and nickel. So what we need to do, we need now to subtract it. What is the delta V with respect to hydrogen? So we know that nickel is over here, and we know that nickel is above iron, making nickel more cathodic and iron more anodic. So we need to write down the voltages. So the V naught, okay, so solution. Okay, so in this solution, we're going to have our V0 of nickel couple, so nickel element, is going to be negative 0.25 volts. Then we have the V naught of iron, 2 plus iron, is negative 0.44 volts. Okay? So we know that iron is going to be more anodic. So we denote that this is our anode. Or sorry, this is cathode. This is the anode in this reaction. Okay, so what do we do now? in this chapter, we also have another equation called Nernst equation. Here it is. This is the equation you will be using, and it's going to be given to you, obviously. So you have gas constant, R, it's going to be given to you. You have Faraday's constant, okay, I think 86 something thousand coulombs per mole. N is going to be your, what is N? Does anybody remember N? What is N? Number of atoms, okay. Electrons? I guess it makes sense, maybe. We'll figure it out. And we have the molar masses, okay? Molar masses, M1 or M2. So, delta V, you see this? V20 minus V10? That is the EMF, standard elements, electric potential. That is the difference. We need that. All right, so we know that this is a cathode, this is a anode. So we're gonna have delta V0, delta V naught, being produced as, I'm gonna bring this up, as V2, oh, crystal green, yeah. All right, V cathode minus V anode. It's always V cathode minus V anode, okay? So V of cathode minus V of anode, okay? You put them together, what do you get? Negative 0.25 volts, negative 0.44 volts. What do we get? We get positive 0.19 volts. Important thing, if you do mess up on cathode or anode and you don't know what you're doing, if you compute your delta V not being as negative, then flip it. Your cathode will be anode and anode will be cathode. Why is that so? Delta V naught is essentially like a Gibbs free energy for solidification. And what I mean by that, if it's positive, it's going to be a spontaneous reaction. It has to be positive to be spontaneous. And it has to be spontaneous in order for this to work in this configuration. Let's say on the midterm or final you mess up. You say this is anode, this is cathode. Then you calculate this, and you're like, why is my answer negative? That's because you have to flip it. And only then you can continue, okay? That's a good sanity check for you guys. All right. Now, having said that, we now need to use the Nernst equation. Yes, and if you do mess up again, if you don't do this check, in your Nernst equation, you're going to divide the concentrations basically inverse. It's going to be totally wrong. Yes. You're going to better. I'm doing this for the sake of the concept. Okay, that's how it should be. Numbers, I don't care. Whatever the number, it has to be positive. If it's negative, you did it right. If you don't get it right, if you don't do this check, you go into Nernst equation. V is delta V naught minus RT over N, Faraday's constant, natural logarithm of your anode over cathode. Anode over cathode. And like you do mass, you're like, oh, iron will be cathode. Well, your answer is totally wrong, okay? So that sanity check is fantastic. You have to use it. All right. So we basically plug all the numbers in. Well, not really. We'll have to reiterate the equation. We can for temperature. We're looking for this temperature. We need to write down gas constant. Gas constant is 8.314 joules per mole Kelvin. Your Faraday constant is 96,500 coulomb per mole. And that is it. So we have to now isolate for this. I would suggest you to not the wrong equation. Just calculate this first. Calculate the natural logarithm of your concentrations. So that's going to be what? That's going to be natural logarithm of 0.1. So 0.1 divided by 0.3 times negative 3. Right, so you can compute that first. It's going to be a number. So then you can reiterate that. We know this number is positive 0.19 or 0.21, whatever it is. It's some number. This is also a number, 0.14, isn't it? Yes, 0.14. So you move this one here. your negatives cancel out. You have some number, and you basically reiterate that for T, and you find your T. Okay? Your T will be in Kelvin. It will be in Kelvin. Okay? So you need to convert it to Celsius or leave it in Kelvin, up to you, unless you are asked otherwise. Okay? So from here you find your temperature and then you're done. That was one of the final exam questions. Do not mess this up. This is where people had the problem. Yes. And I'm not sure. Let me look it up. It should be on my PDF file. Number of electrons transferred. Oh, so it has to be 2. It has to be 2. Why is it 2? Actually, no. Let me check that. I don't know. I'm writing it down. Yeah, n is equal to 2. Thank you. So the reason we have n is equal to 2 is because in this reaction we have nickel given up 2 electrons and iron gaining 2 electrons. They have the same valence. They have the same electron transfer, so it has to be 2 here. So when you plug all the numbers in, you have n is equal to 2. You have, so yeah, it has to be 2. Basically, if you have, let's say, something with 3 electrons, right, transmitted and 3 gained, the total is not 6, obviously, it's 3, because you're depositing 3 by losing 3 electrons, okay? So n is the number of electrons in the electrochemical reaction. All right, so this is, again, you just reiterate that equation, pretty clear. All right, let's move on. Another question for you, and then we're going to move on to midterm chapter. Ask for this question. And we're going All right, the next question, question 4, yes. I don't hear you. All right, guys, can you come down, please? Thank you. I have a question. Yes. So you're saying if the number of here would be a number different, that reaction will not. You would need to balance it at the end. You would have. Okay, that's a good question. Can you look up an example? Can you look up an example of reaction, and then tell me? I'm going to solve the second question now, and then I will try to figure out the answer to your question. Yes. All good? Oh, there's a message. Thank you. All right, let's resume. Not a lot of time left. Where is my razor? Here we go. All right, so the question is asking. Magnesium chloride. Okay, let me solve this one and I'm gonna get back to you, okay? All right, last question for this chapter. Electrochemical cell is composed of pure copper and pure cadmium. Electrodes immersed in solutions, okay, of their respective divalent ions. For a 6.5 times 10 to the power of -2 blah 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 concentration of cadmium, the cadmium electrode is oxidized, yielding a cell potential of 0.775 volts. Calculate the concentration of copper. Okay, so again, you have one equation, Nernst equation, and you can again ask AI to give you values to reiterate for one solution, for another solution, given this and given that, okay? So RT over Faraday times N multiplied by natural logarithm of your anode over cathode. So in this question, we know that cadmium will be the one anode, okay, and the who is that? The copper, it will be the cathode. Okay, and we are asked to find the concentration of copper. Okay, so you can imagine you have to go through the shenanigans of the right? The electrolyte. You'll have to find from here. So you would have to isolate for this. So it would be delta V naught minus delta V equal to RT over NF. Natural logarithm of cathode over anode. Okay, from here you have NF times delta V naught minus delta V divided by RT equal to natural logarithm of the cathode anode. Okay, how do you get rid of the logarithm? You put it all to power E. So you have e to the power of NF times delta V naught minus delta V divided by RT is equal to cathode over anode. All right, now we can fully isolate for, what are we looking for, cathode? Yes, copper. So copper will be equal to this E, NF delta V naught minus delta V divided by RT times anode, which is cadmium. All right, that's the final equation. You plug it in, you plug into it, and you're done. Okay, so that's how you reiterate this to show you the process. Okay, so that's how you come from here. You go to that. It has to be E exponent. Okay, e to the power of NF. Okay, now how many electrons are being transferred in this process? 2. So we have this reaction. We have cadmium plus copper 2 plus is equal to cadmium 2 plus plus copper. Okay, so we have 2 electrons being transferred in total, and N is equal to 2. Faraday's is whatever. R is known. T is known in this question. Is it known? Yeah. 25 Celsius. Delta V is known. Not delta V is known. This is known. Good. Question. How did I answer? Square bracket means concentration. It's called molars. It's grams per liter or something like that. So, yeah, so you do that, and then you go through this process over here. And then you go from here to there. Well, I don't think your question. This is just like converting natural logarithm to, linear functions. CD is cadmium. CD is the standard cadmium. Yes. I'm not going to announce it right now. It's a lot of questions. Yeah, good catch. Yes. So, yeah. So there was a mistake that I made in the anode cathode, okay? All right, guys, calm down, please. Not a lot of time left, okay? We have anode and we have cathode, okay? I made a mistake over here in the ratio. I later when I did my derivation. Basically, I get by the cadmium. Divide, okay? That's all coming from the Nernst equation, all right? So that's that. Now let's get to the question of imbalance of electrons, right? You define the reaction, you said sodium and what? Or magnesium and chloride? Okay, let's look up EMF, what it is. And that was the last corrosion question that I had. So we're good to go for the next one. All right, let's see if I can figure out imbalance. Okay. Okay, so we have magnesium and chlorine, you said? I don't have a chlorine here. Okay, let's say it's magnesium and aluminum. Magnesium and aluminum. So how many electrons choose then, right? Aluminum 3, 2. We need to write down a reaction. Okay, so it would be aluminum plus. Let me bring this up. You have 3 electrons being released and 2 electrons being acquired. I think it's sure. What the lost and gate? You mean? Yes. Yes. Look, aluminum is losing 3 electrons, and magnesium is gaining 2 electrons. It has to balance out. So how does it balance, right? That's the question. Would it be what?
Do you know the different forms of corrosion, like uniform attack, galvanic? It wasn't covered on
Your name? Are you? Oh my God! I should know. Yeah.
Corrosion that I didn't see that were on the slide. Somebody. But I didn't these are the 2 things I didn't see.
Yeah, just go over his slides. Again, you just have to know what it is, pretty much.
So
No worries.
Do you think it's one where we have to balance it?
I'm thinking about this right now. I actually don't know. 3 aluminum, 2 magnesium.
I feel like no, right?
I'm debating how many electrons should be in the transfer, whether it's 6 or it's 1 actually.
6 or 1.
6 or 1, yeah. It could be either that you have to balance it out by multiplying by a factor of 2 and 3 to make it a total of 6, or you just find a different. I'm more inclined to say that it's 6 in total, but I might be wrong, so I have to answer this right now. All right, guys. Now the solution to this question. All right, guys, calm down. All right, guys, please stop talking, please. All right, thank you. For the question, I think you need to balance it, okay? So I think you need to multiply by a factor of 2 and 3 to make it a total of 6 for the balance, okay? Now, my speculation is that it has to be 6 in total, but I might be wrong. So I will look at it after the midterm study hall. It's a very good question. Thank you so much. My speculation that it's 6, I might be wrong. I'll have to look into it. It's a very good question. Thank you. Yes, again, to those who were talking a lot, the question was that magnesium reacting with aluminum. What happens? We have an imbalance of the electron transfer, 2 and 3, right? So, yes. 6. Okay, so I guess my hypothesis, I would call it, was right. It has to be a balance. So, thank you so much. You saved my evening time. So, 6 has to be preserved by the mother nature. Okay. All right. So, we're finally done with the content of the midterm study hall. We shall now to the remaining 3 questions, which were. Yes, so well below diffusion. All right, diffusion question. So, listen carefully, okay? If boron is diffused, guys, please. If boron is diffused into a thick slice, okay, so diffusion, guys, have to click in. We have Fick's law, right? Fick's law, we have linear Fick's law and non-linear. So, I guarantee you're going to have on your final exam a question where you will need to use that table of the error function. You remember the error function? Yes? Yes. So we have z and we have ERF of z. Okay, so we will need to use that to calculate our diffusion stuff. So just to get to the bottom of it. All right. For those interested, the error function itself looks like this. It's the 2 over root pi, the integral from 0 to z of e to the y squared y. Okay. You should be finishing right now. Doing integrals in Calc 2? Yeah. Okay. So polar. You're familiar with that crap, right? All right. That thing. Use the solution to that equation. You will get a table. Okay, a table with all the answers. So if you pass your z to this function, go to your polar coordinates, blah, 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 and you will get the ARF of a particular value, right? And you have that table, which is going to be given to you on your final exam. Now what the question is, right? Question is as such, so let's write down given. So if boron is diffused into a thick slice of silicon, so we have a thick slice of silicon, and we have a boron, which will be diffused. Okay? Which will be diffused with no previous boron in it at a temperature. So no previous boron means that the initial concentration is 0. You have to read the question. C0 is equal to 0 per centimeter. If boron is diffused into a thick slice of silicon with no previous boron in it at a temperature of 1100 Celsius, for 5 hours, you need to convert hours to seconds. That would be 5 times 3600 seconds. So that's 1.8 times 10 to the power of 4 seconds. Okay? What else are we given? What else are we given? We're given the fact that what is the depth below the surface at which the concentration is 10 to the power of 17 atoms per centimeter cubic. So we are looking for that depth. So that's the Cx. The x will be the depth. So we know that here C0 is 0. We know that Cx at some x, we're going to be looking for x. And we know that that Cx is something. We also will know that if the surface concentration is 10 to the power of 18, we also know the surface concentration. So the Cs is 10 to the power of 18 atoms per centimeter cubic. We also know the Cx, which is 10 to the power of 17 centimeter cubic. We have the diffusion constant, or the diffusion rate, sorry, that's the d. The d is 4 times 10 to the power of negative 13 centimeters squared per second. Okay, fantastic. So we need to find the depth. So the depth, F. What is the depth? Okay, so we use the Fick's law, the second Fick's law, which is nonlinear. As soon as you see the error function, second Fick's law, 100%. So to begin, let's write down the solution. I guess I will start here. So the equation is as such: Cx minus C0. Okay, I'll have to write this one properly. A couple of things I expect from you. So first, second Fick's law. Okay, you have to write it down. Fick's law. What is the second Fick's law? Cx minus C0, Cs minus C0. Luckily for us, all of that is 0. Equal to 1 minus error function of x divided by 2 root of dt. Okay. So Cx over Cs is equal to 1 minus E x 2 root d. Okay, so what do we know? We know Cx, we know Cs, we know d, we know ERF later, and we're going to find x. Okay, so the question is pretty simple. So, cool. Let's find now what is this, ERF. We move the around, we get ERF of I'm going to call this E. all of it is going to be is equal 1 minus Cx over Cs. What is our Cx? 10 to the power of 17. What is our Cs? 10 to the power of 18. So when you divide both together, you get 0.1, right? It's just 1 over 10. So that's going to be 0.9, basically, at the end. Okay, so you just divide 10 to the power of 17 over 10 to the power of 18. Okay, so that's 1 over 10, essentially. All right, so we're coming back here. Now on the final sheet, you're going to be given a table. So linear interpolation shall begin. Basically, what you need to do is you need to find the two values in between which you have this number of z. So the nearest numbers that I had were function, right? So it has to be y of z be equal to this. And we need to do the inverse of ERF to find the z itself. So we need to find what is this z that will give us the 0.9, given the fact that we have 1.1 and 0.8802, and the upper value, upper bound is 1.2 and 0.9103. So you just simply go and see which of the two values between I can plug in this value in order to find my z, okay? You have to use linear interpolation to find your z, okay? How do we use linear interpolation? We use slopes, okay? So z minus 1.1, okay, divided by 1.2 minus 1.1 is equal to, now corresponding y values, 0.9 minus 0.8802 divided by 0.9103 minus 0.8802. And this step must be shown. Must be shown. You cannot skip that step. If you do, you're not going to be given part marks. Every year I see people not showing this, and even if you get your z correct, you didn't show this. Okay, you must. Now, when you do this, the next step will be obviously the z, which is going to be equal roughly to 1.1631. Okay, is this somewhere in between this and this? Yes, it's somewhere in between this and this. And that's good. So we found our z. What did we denote our z as? X over 2 root dt. Isn't that true? Yes. We were able to find the argument of the function, right, by doing the inverse on the function. Thus we found the argument. So we have x and this. Okay, we're pretty much done. We have diffusion coefficient or rate. We have the time. We have this, and now we can find x. So simply reiterate your equation, and you're going to get x of 1.97 micrometers. Okay, so micrometers, that's 10 to the power of -6. That's how deep this boron at that concentration is going to go into our metal. Okay. Any questions? Yes. First what? How did I get the what? That's going to be in your table. You just you just look. Yeah. No, I would just like for your general knowledge. Yeah. Yes. dt. You mean yeah. E is your diffusion rate, t is your time in seconds.
So do we? Is it a multiplication?
Yeah.
Oh, d times t.
Sorry. Yes, d times t. Okay. Yes. Yes, one of you guys. You begin.
Is the linear interpolation formula given?
You know, if it wasn't recording, I would have said something. Dude, it's linear interpolation. It cannot be given. It's like grade 5, 6. Really? That linear interpolation? It's just linear interpolation. I mean, guys, come on. First year engineering. You will have to. You will have to do some unit shenanigans. You might get either millimeters or micrometers, some stuff. Again, just know your units. Yes.
So like these multiple, are they just multiple choice questions from like the past exam?
Are there, sorry?
What are these like multiple choice questions? These would be multiple.
This multiple choice? No, there's no way.
Because you said we were gonna do multiple choice.
Later, yeah. This is not the multiple choice. Okay. C. Yes. Yes. Oh, sorry. Z. Are there any units for Z? So that is a meter divided by the centimeter divided by the centimeter over 0. All right, no further questions. Then we're gonna move on to the phase diagram question. Oh yeah, of course. Okay, no way it's multiple choice, right? Question for today. All right, guys, last question for today will be the phase diagram, okay? We'll have to conclude with chapter 9. All right, phase diagram. So the question is that we have 1 kilogram of an alloy of 78% lead and 30% tin, which is being slowly cooled from 300 Celsius. Calculate the following. Okay. Draw the phase diagram, and here we're going to figure stuff out. You will be given one of the phase diagram questions for sure. It will be 100% there. So phase diagram, we have lead and we have tin. And that is the composition of tin. Weight percent tin. So we're given the 30% tin. So it's somewhere here, okay, 30%. The diagram is as such. This goes into the eutectic point. Okay. Our solidus, solvus lines, all that stuff. So we come from here, and we go right here, and we go right here. Okay, so this is 18.3% of tin. This is 61.9% of tin. This is 97.8% of tin. This is eutectic at 183 Celsius. We are at 30%, somewhere above here. We need to draw a vertical line as step number 1, as we always do, vertical line. We are somewhere way above here right now, okay, 300. We are so-called superheated. There's a word for that, superheated. When you go to this point, you liquid, but if you get way above it, you're superheated. If you put too much of the superheat, you may vaporize your lead, and you will breathe it, and you will probably die because it's toxic. So, 300. Now we're what? We're slowly being cooled, aren't we? So we're being slowly cooled. Now we have to figure out a couple of things. Check. Okay, so the mass fraction of the liquid in pro-eutectic alpha at 250 Celsius. So at 250 Celsius, which is around here, okay, we need to figure out the mass of the liquid and pro-eutectic. So what does pro-eutectic mean? Pro-eutectic means that you are over here in this region. Basically, you are here, which makes sense, pro-eutectic. Hypo-eutectic means that you are over here in this region. Okay. Anyway, basically, that's what it is. So there's This is a primary, so we need to find the mass fractions, and we also have the mass of the alloy, 1 kilogram. Okay, and we 30% tin. That's what it is, 30% tin. So the mass fraction of the liquid and proeutectic alpha at 250. So at of 250 Celsius, what is the mass fraction of the liquid? WL and W alpha. Okay? So, lever rule. So we have a vertical line being produced over here. Now we need the horizontal line. We have now the vertical line, 250 Celsius. Okay. Now, next step will be to figure out our C0, right? So this is our initial concentration, 30%. This is our C0. We have liquidus, and we have solids, okay, over here. So that's going to be our CL. That's going to be C alpha, because this region is full of alpha plus L. This region is just alpha. This region is beta plus L. This region is just L. This region is all alpha plus beta. Okay? And that is obviously beta over here. Okay, so we're fully now constrained. Cool. We know that this is C alpha. We know that this is CL. Now we need to go and drop our vertical lines on these points over here and over here. So obviously my graph is not to scale. So from here on the actual graph on your final exam sheet, if it is given, and it should be given, you will have this being located on the tin axis at roughly 33.1% of tin, so very close to your initial value, very close. That means that you have a lot of liquid, okay? So, and W alpha. So that's going to be our C alpha. That C alpha over here is 12. 12, so that's quite far away, okay? So, now lever rule. We have this and this. These two distances, so this one and this one. And as you might remember, when we do our W alpha, so we're looking for the amount of solid phase in the semi-solid solution, then we take the ratio of the liquid portion over the entire region. Liquid over entire to find solid. To find liquid, we take the solid over the total area, the total length. Okay? Again, I will repeat that. For the lever rule to be true, if you want to calculate the liquid state, you take the amount of solid and divide the length of it and divide the total length. If you're looking for the of solid, the liquid and divide by the total length. So to reiterate that in the equation, to re-articulate it, we have our x, or C of L, minus C of 0 divided by C of L minus C of alpha. C of L minus C of alpha is this minus this to get this, the total length of that region. Now, the alpha is the amount of liquid that we need to divide by the total length. So it's the CL minus the C naught, amount of this region over total region to find the alpha. So it's inverse logic here, okay? This to find this, and if we want to find the W liquid, well, obviously it's going to be 1 minus W alpha, but if you want to look at it from the equation perspective, then that's going to be C naught, right, minus alpha divided by the C minus C alpha. Okay, so the denominator does not change the total length. The top. Okay, so numbers in, we get 33.1 minus 30 divided by 33.1 minus 12. So we get 1469, 14.7% of solid, which makes sense because we're very much close to the liquidus region here. If we were down here lower, that would imply more of solid and less of liquid, because we're here to solidify from the eutectic line to solidify into alpha plus beta. But yet we're here. So we're very close to liquid. Best at this temperature. So you expect the higher portion of liquid over alpha. Meaning that WL is simply 1 minus W alpha, which will be just 1 minus 14.69, 853. So 85% of the alloy is being in liquid state at that moment in time as we freeze our metal. Part B. Part B is the mass. What is the mass fraction of the liquid? Okay, we're looking for, yes, the mass fraction of the liquid and pro-eutectic alpha just above the eutectic temperature, and the weight in kilograms of these phases. Two questions in one. First, let's find what's going to be the W alpha and WL right above the eutectic point. Just right here, literally on the eutectic point. Okay, it doesn't matter. It's like a nanosecond before it. A picosecond, okay? We're here. So now we have this region, and we have this. We already have these, okay, the interesting numbers, 18.3 and 61.point. Plug it back into the equation. What do we get? W alpha. So we're looking for the alpha region, which means that we need to divide this by that to find the L region, this by that. Okay, the counterintuitive approach. So that's going to be our CL minus C0 over CL minus C alpha. So we get 6.9, the point, 30, the point divided by 61.9, the total length, minus 18.3. Yes, 18.3. So we get an alpha of 45.2% weight percent. So the W of L will be about 50. What's that going to be? 54.8%. Okay, weight percent. So that's right above the eutectic point. Okay. Yes. Yeah, it's the same formula, but your concentrations are going to be different because your temperature was different. My formula is the same. Concentrations are different, yeah. Because here, my C alpha are here, but now my CL and C alpha are here. So my concentration, but the formula is the same. All right. So now we need to create the mass. Okay. Take a genius with 1 kilogram. It is assumed to be 1 kilogram. We multiply 0.452 by 1 kilogram. So we're going to get 0.452 kilograms, and that's going to be 0.48 kilograms. So again, it's just nothing. You just multiply by a number. By 1 kilogram. You get 452 grams and 548 grams. All right, and the last question is part C. We need to find the weight in kilograms of alpha and beta formed by eutectic reaction. Okay, we need to find now this. Alpha plus beta. Okay, now we need this. So the approach for this will be a little bit different. We now have a eutectic reaction happening. Okay, so we're no longer concerned about our concentration, because now we have a eutectic concentration locally. So we're over here. Because now we need to find alpha plus beta. We need to find alpha and beta weight percent. So how do we do that? So to find the, okay, so to find that, we just simply need to subtract. So if we're looking for alpha, okay, we need to find the 97.8 minus 61.9 divided by 97.8 minus 18.3. Can you please stop talking? 97.8 minus 18, that's going to be the total length. So what do we get? 97.8 minus 61.9 divided by 97.18.3. It'll be something 0. Some number, okay? Now W beta is simply 1 minus W alpha. That is it. You're done. Again, it depends. You need to pay attention to the temperature and the reaction that is being produced. So the first part was, hey, I have a 300 Celsius being cooled to 250. Could you compute, please, for me the amount of liquid and alpha? Sure. Now, what happens at eutectic point, right when you're about to solidify? We got this. Now, the question is, say, if in the concentration of your solidus front, there is a 61.9% of tin, what's going to be the eutectic reaction in order to produce your alpha and beta in this particular condition? Now you have this entire tie line of the beta region spanning to alpha region, where you have to find the portion of this over that and the portion of this over that. Okay? Any questions? Yes. Yeah, and yes. And then in order to find your mass, you just simply multiply this number by 1 kilogram, and that's it, pretty much, because literally it's a weight percent, so it's just multiplied by mass. Question? To post this one? Oh, sure, yeah, it will be in the solution provided. I haven't posted the solution yet. Okay, guys, cool. So any other questions? Yes. Part B was what happens if we are at eutectic temper. Because we're at eutectic point coming from liquid plus alpha. We're in this temperature. So we're still in this region. Yeah. So what happens when they converge with tri line or with the eutectic line? It's here. I'm nanosecond before the eutectic point, which means that like if you zoom in 100 billion times, I'm still here. And I'm still here. But you're like right there, so yes.
What's part C?
And the part C was, so part C is, let's say you have a eutectic reaction happening, a eutectic reaction. You now ignore this. Let's say you have a eutectic reaction. How much alpha and beta you would produce if given this reaction. Okay? All right, yes? Will we have what? Grain size determination. You could. Yeah, the 2 to the power of ng minus something. Oh, you mean that determining the grain size? Oh, no. No. That's just an assignment question, yeah.
Is being able to draw the graph part of the question, or are we given?
Oh, yeah, given, obviously. Yeah. Imagine doing this for ceramics, right? Anyway, yes. How to calculate Burgers vector? Well, what is a Burgers vector? So that was one of your final exam or midterm questions. What is the magnitude of a Burgers vector, guys? It's what, sorry?
The last parameter divided by 2 times the root of a squared plus a squared plus l plus l.
Is it?
Yeah.
I guess it is. I thought it's just one diameter of an atom.
I don't know.
It should be one diameter of an atom. Maybe your thing applies when you have some screw and edge dislocation happen at the same time. I don't know, but that has to be 2 radii of an atom. That's but I see. Dislocation is just a shift in the atomic lattice, and that shift is denoted by one. That's what Burgers vector is. You just have edge dislocation, right? And it's one atom.
What's the difference between eutectic alpha and primary alpha?
Eutectic alpha is the alpha that occurs right at this point. Okay, so I don't want to overcomplicate the answer to this question, but there's a large answer to this question. That depends on something called local solidification front. On your come to me after midterm, the study hall.
Yeah,
I will explain this.
It was on your study study hall, like for the midterm, I was doing it, and I was like, what is primary eutectic alpha?
It's a long answer to this question.
Is it something I can expect for the final or
No. If you want to learn more about the theory, come to me. Right. So, any other questions before I stop the recording? No? All right. Okay, guys. We have concluded the entire course. Congratulations. Fantastic work. So we're done. To those people who are online, good luck on the final exam, and we'll see you soon. Thank you.